Good morning, everybody, and welcome to the second day of our virtual dam owners workshop presented by the Maryland Department of the Environment Dam Safety Program. We've got about 130 folks online, and people are signing in as we come. So we'll pause for a few extra moments to let the people into the room, and then Jennifer Smith will get us started for today's workshop. Thanks, and sit tight.
Good morning, everyone. Thank you for joining us today. Welcome to MDE's Virtual Dam Owners Workshop. It's a lovely day for a 4-hour workshop on dam safety. This is the second of 2 sessions hosted by the Maryland Department of the Environment Dam Safety Divisions, and my name is Jennifer Smith. I am the manager of the Sediment, Stormwater, and Dam Safety Program, which is one of 8 programs in the Water and Science Administration of the Maryland Department of the Environment. MDE and our Dam Safety Division staff are very excited to offer this workshop to you, our dam safety community. You all represent our owners, operators, designers, emergency managers, and engineers. Once again, we have over 200 currently in attendance today. First, I do want to note on Tuesday that we received a number of questions, and thank you all for that wonderful participation. Unfortunately, we were not able to get through all of them in the 4 hours that we had available. So today we hope to get to the remaining questions and others that you may have today during today's workshop. First, again, I must go over some important workshop housekeeping items. The format for today's workshop will be the same as the one we had on Tuesday. We have scheduled anywhere from 15 minutes to an hour for the sessions today. And again, there will be a 5-minute break between the sessions. At this time, please locate the question and answer function on the toolbar at the top right of your screen and use this to ask questions or make comments throughout today. We will have a time for question and answers at the end of each presentation, and then there will be additional time at the end of the day for question and answers. We were fortunate on Tuesday to have very few issues with using Microsoft Teams, but I do want to suggest that if you lose connectivity or sound, please sign off and then log back into the Microsoft Teams session. So on Tuesday, we've covered a number of topics: how to hire a dam engineer, lessons learned from the FEMA High Hazard Potential Dam Grant Program, the dam safety permitting process. We talked about the dam ownership and enforcement. We discussed safety issues at dams and a number of dam safety guidance documents that are now on MDE's website. Today's agenda is going to be a little bit more technical. We have 5 topics to cover. Our speakers today will be John Roche, Scott Bass, and Charlie Wallace, who will cover technical topics including the basics of geotechnical investigations for dams, dam overtopping protection, dam construction, and an introduction to the Maryland Probable Maximum Precipitation Update. And then Ray Barr will wrap up today's workshop with a final question and answer session and closing remarks. We hope you enjoy the presentations today. For some of you, this will simply be a refresher of what you already know, and for others, this will be new information. So let's get started with John Roche and a discussion of the basics of geotechnical investigations for dams. John, are you ready?
Yes, I am. All right, thank you, Jennifer, and thank you for everybody who's in attendance today. I was joking recently that, I could spend 4 hours, ask any geotechnical engineer to talk about drilling and sampling, and we could spend a lot of time here, but we've got 45 minutes, and what I want to do is just give some high-level understanding about the risks associated with drilling an embankment dam, ways to mitigate that risk, and then some of the things we look for when a permit application comes in to the department to approve drilling in an embankment dam. We'll have a little bit of time to touch on some logistics of the drilling itself, but we're not going to go into any in-depth discussions about drilling and sampling methods, laboratory testing, or analysis afterwards. And that's something we could certainly spend some time on in a future presentation. So let's have at it. One of the first questions we get a lot of times is, how many holes should I drill? Right? And the image that comes to mind is like a Swiss cheese embankment. An engineer might approach us, how much and how many and where and how deep? And that's probably not the appropriate first question when it comes to drilling an embankment dam. First of all, that's the question that should be answered by your knowledgeable geotechnical engineer. I'll probably say this a few times, but the scope and magnitude of a geotechnical investigation depends on the questions you need to answer, and therefore it really needs to be scoped and scaled appropriately by a qualified engineer. So just blindly drilling holes in an embankment dam is risky, first of all, but it may not even get you the information that you seek. So let's talk a little bit more about that risk and dive into that more, because I think there may not be a full appreciation of the risk. Drilling in dams, and whether it be a small pond up to a large high hazard dam, is a serious business. There have been many cases of failures or incidents associated at dams because of drilling or other invasive activities at the dam. And I'm going to say drilling throughout this whole presentation today, but that includes direct push sampling like a cone penetrometer or other in situ testing devices. It includes test pitting, hand augers, all of the above. But really the traditional way to get good geotechnical, geological data is your hollow stem augers and standard penetration testing. So we'll call that drilling. But as an example, here's what looks to be a beautifully maintained dam embankment in New York State. It's a high hazard dam. And in 2015, there was a pretty big news article about this because a severe incident happened. The engineering team was doing subsurface investigations at and near the toe of this dam. I believe they were looking to install a powerhouse and a hydroelectric penstock, retrofit this dam. My understanding is that they knew that there was a confined aquifer type system in the local geology here. But for one reason or another, the drilling at the toe of the dam punctured that aquifer, and they weren't really prepared for that. And when you're dealing with a confined aquifer, you get something maybe referred to as artesian conditions, basically upward flow, upward gradients of seepage. So they broke through that confining layer, and later that day they noticed in that channel downstream of the boring large plumes of muddy seepage coming out. So that muddy seepage is indicative of some kind of erosion, either of the dam embankment or the foundation itself. Well, that's a really bad thing, right? That's an internal erosion failure happening, and that can rapidly lead to a full dam failure. So what happened as a result of this? Well, they activated their EAP. They began 24/7 monitoring, which I believe lasted for months. They had to drain or partially drain the reservoir as a result of this to lower the risk. If it failed, less water would be less risk downstream and less consequences, but also to lower some of the hydrostatic pressures. And then they had to have an emergency procurement for installing relief wells to relieve some of that artesian pressure, and a significant grouting program to seal things up. Of course, this cost a significant amount of money, seriously delayed their project, put people downstream at significant risk, and really was just a bad thing for the dam owner to have. And this is, just one case study. There are many other case studies where drilling in embankment dams can cause problems. And sometimes it's important to realize that those problems may not be evident right away, particularly if you're dealing with, let's say, a dry facility, a dry stormwater management or flood control facility. So drilling in dams is serious business. Let's talk a little bit more about what can go wrong. So the first bullet point I have here is some general advice. There's some kind of general industry consensus in the dam safety world about drilling in embankment dams. And we write this right in our permits when we issue a permit for drilling. Drilling into or close proximity to a dam or levee embankment is an inherently risky activity. Again, I want to drive that message home. So some of the big picture things that we all should be agreeing on is we should avoid drilling into the core of the dam unless absolutely needed. All right, that core, that impervious core, is the water retaining element of our dam. It's that line of defense to prevent against seepage and allows the dam to hold back the water itself. And a lot of times I'll mention, I see that particularly for retrofits these days, which is a hot commodity in the stormwater market, if we don't have adequate as-builts, Charlie's going to talk a little bit about as-builts as part of the construction later on today. If we don't have adequate as-builts, the first thing people do is they say, well, let's poke some holes in the dam embankment and see if we have a core or not. Well, realize that when you're poking the holes in the embankment, you're literally poking holes in the embankment. Drilling through that core can cause significant damage, particularly if you're not careful in drilling methods and in drilling closure as well. So our suggestion, avoid drilling into the core unless you've weighed the risks, mitigated against the risks, and it still provides worthwhile information that the benefit cost ratio makes sense for that risk. The next consensus is that drilling and test pitting down the downstream toe of a dam is also one of the most riskiest spots because of seepage gradients and pressures that may build up. You must have materials available and trained personnel on site who know how to react and respond to an emergency if you get, let's say, a seepage incident like at that Cannonsville Dam in New York. And then lastly, kind of a big picture industry consensus that we'll talk about as a baseline is putting piezometers in the core of the dam is generally not going to provide you with the data that gives you significant additional understanding of the structure itself. Putting a piezometer in the upstream or downstream shell of embankment gives you great information. But by the nature of the impervious soils and lag times to get actual responses of phreatic surfaces, piezometers in the core are maybe not the best idea. And that kind of goes hand in hand with avoiding drilling in the core. All right, so that's some general advice, but let's talk about more about what can go wrong if we drill an embankment dam. And after we've talked about what can go wrong, let's talk about some hazard mitigation strategies. All right, so one of the first and foremost things that can go wrong when you're drilling an embankment dam is called hydraulic fracturing. And hydraulic fracturing occurs when you introduce a drilling fluid into a drill string. And you've introduced that fluid, it could be air, could be water, it could be grout, it could be drilling mud, but you've introduced that and now you have a pressure, a fluid pressure that could overcome a low confining stress and literally fracture the dam embankment. So this is one of the reasons why we say we should avoid using drilling fluids whenever possible, because of this concern about hydraulic fracturing. It's important to note that hydraulic fracturing can occur in all materials. It can occur in cohesive or cohesionless materials and bedrock, and it can have detrimental effects on both the embankment soils itself and the foundation soils, either one of which, if they're fractured, can cause or contribute to initiation of an internal erosion failure mode. So how will you know if you've hydraulically fractured your dam embankment? Well, this is where an experienced driller, an experienced drill observer comes into play. You would notice things like a loss of fluid circulation. You'd notice, a blowout maybe of drilling fluids into adjacent boreholes or in instrumentation you've already installed, or in seepage at the face of the toe or face or toe of the dam. Again, sometimes drilling with fluid is necessary, like rock coring, where you need to cool a core bit, but to avoid hydraulic fracturing, the easiest way is to avoid introduction drilling fluids in the embankment. And just as so we're aware, locations that are particularly sensitive to hydraulic fracturing, those where there's low confining stresses, are areas that may be adjacent to steep abutments, near spillway conduits, or anywhere where there might be some kind of natural or man-made discontinuity within the embankment structure that could cause differential sediment or things like that. All right, a similar problem that can go wrong with drilling, and it's similar to hydraulic fracturing, is pure and simple erosion of embankment or foundation materials. Imagine again, you've introduced a drilling fluid into the drill string, and there's some kind of latent defect or crack or things in the in the embankment itself. Well, that fluid, that circulating fluid in the drill string, can actually just start eroding that material. And again, this is a perfect example of an internal erosion type failure mode, where that erosion, if that, depending on the nature of the soil and the amount of fluid that's circulating, you could actually eat away large portions of the internal structure of a dam embankment or foundations, and that would be a very bad thing. So the keys, the things to look for erosion is and the locations where erosion can occur is very similar to a hydraulic fracturing. It's areas where there might be low confining stresses or where defects are likely. So anywhere where there's a discontinuity in the embankment. And again, it would be evidenced potentially by loss of drilling fluids and things like that. So two hazards that can go wrong with drilling. Another one, and this plays into that Canonsville example, is artesian conditions or blowout of your boring. In this case, it doesn't necessarily have to be fluid introduced. This could be drilled in dry using hollow stem augers or sonic drilling methods, but you perhaps penetrate through a confining layer, and that may not have to be a significant geologic stratum that's confining. In some cases, it could just be the few inches or feet of topsoil and clay soil near the ground surface. But if you've got a vertical seepage gradient through the dam, perhaps maybe you don't have a great impervious core and cutoff or internal drainage, you could start getting uncontrolled seepage out through that borehole. And this is a really risky condition. It is something that a drilling plan needs to consider. And this is a case where you might actually need to put some positive head into your drill string if you think this could exist, or if you start getting loose soil at the bottom of your drill string, you might need to add some water to stabilize that hydraulic pressure, but it's very difficult to stabilize once a blowout has occurred. Now, this guy here looks like he might have excavated through some kind of water main or something like that. But, I've had in my career the distinct pleasure or displeasure, I'd say, of probably drilling through or excavating through a number of different utilities below the surface. And that's kind of similar to artesian conditions. Once you puncture that water main, it's very hard to shut it off. But that water, that force of flowing water, can cause significant damage to your dam embankment. And it's very difficult to stabilize. That's why you need to have appropriate materials and personnel on site to react appropriately to the hazard and try to mitigate it as best you can. All right, another hazard of drilling and embankment dams is contamination of internal filters or drains. Again, this can happen whether you're drilling with fluids or in the dry, although with fluids, it's more likely to cause contamination. But imagine as you penetrate that drill string, you go right through a nice graded aggregate filter inside the dam, and you're either dragging soil particles through the drill string that could contaminate that nice, open, clean C33 sand that's there, or if you're using fluids, that fluid, that mud and suspended particles within it just seep into that and muck it up completely. It's very difficult to fix this once you've contaminated an internal filter. Also important to note that when you seal a boring, and we'll talk more about proper boring completion methods, but you're injecting grout into this under gravity head, you can migrate that grout into the filter medium and clog it as well. So it's very important to know where these features are within your embankment dam so that you can, again, weigh the benefits versus the risks of potentially penetrating through them. Sometimes maybe you're designing a remedial design for a seepage system. You need to know what the gradation of that existing filter media is. But when you do that, you need to take special precautions and special closure provisions to replace any material you've excavated with a similar appropriate filter graded material. All right, and lastly of the hazards I'm going to talk about drilling an embankment dam is the phenomenon called heave. And this can occur when you have maybe an upward seepage or a groundwater gradient that's present. If you're doing it in a soil boring, you may notice that you get very loose soils in your standard penetration testing. You get sample disturbance, and that's invalid data. And you've gone through the risk of drilling through the embankment dam, and if you come out with bad data or no usable data at all, well, that's unfortunate, and it wasn't really worth the issue. Here's an example here in Baltimore City. This is the Guilford Reservoir, and this can happen during excavations as well. The Guilford Reservoir was in early stages of going offline. It was still water-containing reservoir, but if you're familiar with the area now, it's been converted to large concrete tanks that are covered. But here, the contractor was installing a new water main right at the toe of the dam, and you can see really in a heavily populated area, houses, less than a few hundred feet downstream from this high hazard dam. Well, in this area, because of the seepage gradients and the pressures that were built up in the foundation soils, the contractor was digging the trench, and what was happening was soil was actually heaving into the bottom of that trench box supported excavation. But the excavator operator didn't realize this, so he'd keep on digging, and it just felt like he wasn't making any progress because more soil was coming in as they dug. Well, where was that soil coming from? It was coming from the embankment and the adjacent downstream toe area. And you can see on the left picture that those large cracks that appeared, those cracks appeared in the embankment itself and in the adjacent roadway because we're now mining soil basically from the embankment and the downstream toe out of this trench box and causing large settlements and collapse. So that's a big concern. Another reason why test pitting in embankment dams can be quite a dangerous activity and something to be aware of.
Hey, John.
Yes.
I'm sorry to pause you and interrupt you. We're getting word that because your video is on, that it's breaking up the presentation a little bit. So, and I don't know how to turn off your video. Maybe you can do that.
I will turn off the video. That's good for us to know.
Okay, thanks.
All right, let's see how that works right now. And please feel free to jump in again if the problem persists. All right, so let's talk about the scope of your drilling program, because once we understand the risks and we're moving forward with needing to have a drilling program for a dam, we need to talk about how we define the scope appropriately. Again, it's not just how many holes and where. So the first step when you're planning a subsurface investigation program is to define the problem that you're trying to solve, right? So is it a seepage issue? Is it slope stability? Do you need design strengths for new construction? So write those down, document them. What are you trying to solve, and document the objective. Next, what methods are available to solve your problems? Realize that some may be better suited than others. A soil boring only provides information at a single discrete location. So that's true in geotechnical engineering. It's true in a lot of other engineering fields where we have to take limited data and extrapolate it into a model that somewhat represents the system we're working in, right? But a soil boring at a single point in time may not be sufficient to fully understand and evaluate a seepage issue because you only have one location of your phreatic surface potentially. So think about, maybe there's other methodologies. Maybe there's geophysics that might be appropriate, or other type of in situ testing. What kind of instrumentation do you need? Also, it's important to compile and get all of the relevant information. Look at geologic mapping. Look at old drilling logs if there's available. Look at inspection reports and construction records. That can really be revealing on how the embankment itself was constructed if you're trying to solve that problem. Look at instrumentation. So adapt your scope based on that available data. If you can rely on it, maybe you can reduce your scope. If you have a higher degree of uncertainty, maybe as a result of that review, maybe you need to increase your scope because you can't rely on the old data. So use this process here to develop a preliminary plan of action for your drilling program. And this doesn't have to take hours and days. This can be a relatively quick exercise, all right? Now, once you've got that preliminary scope and you think you know what you want to do, please take a step back and weigh the risks versus the rewards. Think about what you're drilling and how a potential failure mode could be impacted by your actions in the dam embankment. So I've got a few listed here, but let's maybe only touch on one or two. Think about if you're looking to investigate the seepage through the foundation of a newly constructed dam or a dam that you're about to construct. Well, you want to investigate the soils and the geology below the dam for perhaps highly pervious soils or bedrock fracturing. You want to determine appropriate cutoff depths. And, you know, because it's an unconstructed dam, it hasn't been built yet, that's a relatively low risk proposition. But then let's look, maybe you've got seepage exiting the downstream face of your dam, right? In an existing dam, you have maybe piezometers, but they only give you information at a single location. You might need to consider multiple piezometers if that's the case. Or maybe geophysics can help you understand the resistivity and water flow within the embankment. Realize that if you put a piezometer in, you're only getting a single point in time. So you might want to think about altering the pool levels and looking at seasonality, just from wet, dry seasons, but also high and low pool levels. So it's a time factor there to get the information you need. It's not just the number of borings, but it's considering those other factors. So can you safely drill this? I would say yes, but there's variable risk depending on the site conditions. So recognize that risk and to think about ways to mitigate it. We all know that there's known unknowns and unknown unknowns, right? When you're drilling into anywhere for the first time, you have to have some room for adaptation and scope change. But the persons who are allowing that adaptation and scope change need to be understanding these risks so that if they do change something, they're not unintentionally causing more harm. So once we've weighed our risks, determine the appropriate hazard mitigation steps based on what you plan on doing. We're going to talk about some hazard mitigation steps in the next section, but I just want to think about, active monitoring of the dam. Make sure people understand what their duties and responsibilities are. Identify a responsible person on the site who can implement those actions. We think it's very important that you have a trained engineer or geologist who is there to log the borings and kind of be in charge of your drilling crew. I know it's so much cheaper to have a drilling crew, especially one you trust, out there on on your drilling job, and they just get the job done and bring the logs and samples back to you. But when you're dealing with a dam, there's so much more risk. You need to have somebody out there kind of supervising the work. And just documentation of all of this. Documentation of your plan, of the hazards that you've identified, of your mitigation steps. They should all be documented in a subsurface investigation plan. Then this doesn't have to be an elaborate document. It can be a relatively short 1 or 2 pages, but it's something that is there. It's a record. It's something we're going to look for in permitting, and it's scalable to the scope of the work, the dam, and the risk. But at least it gives everybody an equal understanding and baseline of what is important. Lastly, when you're out there in the field, execute that program to the plan, right? Understand there may be some adaptability needed. So you might want to build some what-if statements into your investigation plan. If you get something you don't expect, then add a boring at this specific location for these reasons. And have the persons in the field, the drill crew and your geologist or engineer need to understand that if you deviate from that plan without tying back into all those previous considerations, you might expose people to greater risk. Right, so some hazard mitigation strategies. Of course, permitting is a hazard mitigation strategy, right? Because it provides a second set of eyes to look at what you're planning on doing. You benefit from experience of persons who are familiar with a dam and its construction, and they might be able to provide, a backstop to you or a check to what your investigation plan and strategy is. We think permitting needs to be required when you're drilling within the dam or its appurtenant structures and adjacent to dams. And how far, what is adjacent to a dam has been a question that's been asked of us a lot. And frankly, it's not one that results in a very easy answer. So what we're going to suggest is that certainly any boring within 15 feet of the toe of a dam would count as something that triggers a need for a permit. But then also, if you drill within the distance of the dam that is, exceeds the depth of drilling exceeds the distance from the dam. So let's say you're 50 feet away from a dam, but you want to drill a 75-foot deep hole. We kind of thought, that might fall into the same category as well. And, it's important to say that this is for dam safety. Local SCDs should be, reviewing and approving drilling in embankment dams too. We see very often small ponds get a lot of holes poked in them, improperly backfilled, and that may not always be a small pond forever. Hazard creep exists. That could become a high hazard dam with one downstream development. So it all needs to be done properly. All right, another hazard mitigation strategy is to become familiar with and follow the available guidance that's out there. Right now, I'm working on distilling some of these documents from Army Corps of Engineers, Reclamation, and the FERC for their drilling and embankment dams, and making something for Maryland that's a little easier to digest. But honestly, these documents are not overly complex. They're relatively short. They're all fairly similar. I would say we don't necessarily have a preference for one over the other, although I think the Army Corps might be the standard we're having. But know this guidance. It helps explain some of these risk and hazard mitigation strategies. Again, study the dam construction and local geology. Make sure that your engineer and your drillers on the site know what they should expect before they go. Be aware of internal dam features that must be avoided. Can you imagine drilling through an embankment dam blindly and penetrating through a spillway conduit? How are you going to fix that? And who's going to pay for it? That would be a horrible thing. Also understand that local geology can change after a dam is constructed, right? You've got all this water now. How is that changing how water flows through the subsurface? So you have to do this to build an awareness of what is expected versus what's unexpected. Appropriate drilling methods is probably the #1 hazard mitigation strategy. Again, fluids must be avoided where possible. Hollow stem augers are generally the most appropriate method. Again, you can add water a little bit here and there if needed, but realize once you're below the groundwater surface, or if you've added water, you need to raise and lower your tools, your drilling tools in the stream slowly, because you don't want to throw something down there and surge and cause a buildup in pressure for that reason. Sonic drilling is also something that's accepted. It's great for obtaining bulk soil samples. In my experience, it hasn't really been great for having SPT drilling and sampling with it. And the good thing is sonic drilling is becoming more and more accessible these days, even in the past 5 and 10 years. Hollow stem augers, which is great, we're in the mid-Atlantic, that's kind of the standard drilling methodology as well. In other parts of the country, that's not always the case, but we're benefit here. When you're doing rock coring, look at multiple barrel systems to control the water and make a core retrieval easy. We've had suggested and sometimes sealing the rock and soil interface before you core, so that water that you might inject into the drill string at that soil rock interface, especially if you're drilling through hollow stem augers, which have those teeth on it, as you can see, so you don't necessarily get a firm contact with rock. You might want to seal that to avoid waters escaping. And you really need to, again, monitor those fluid pressures in return. Air rotary is acceptable in really limited cases when you've got an open graded rock shell where you basically can't develop any kind of air pressure or overpressure in there. All right, qualified drilling personnel is important. Experience matters in this case. We'd suggest 5 years of experience drilling in dams is preferred, and with the equipment and methodologies that you're planning for your program. That's one of the reasons why we ask for the driller's qualifications and resume as well when you are submitting a permit application for us. Likewise, qualified engineers and geologists. logging it. You may have extensive experience drilling and logging boreholes on all sorts of sites, but if you haven't worked on dams, you may not realize some of the unique issues associated with working with dams. So, and that person needs to be capable of exercising judgment to ensure the work is in a safe manner. So I'm taking an excerpt here from some of those federal guidance documents that give some ideas, and this will all be available later so you can read through it, but levels of experience expected for those persons who are drilling and logging the soil samples as your representative on the site. All right, proper borehole completion is so critical. It is absolutely not acceptable to pack the cuttings back into the borehole. First of all, those borings never pack in all the way. There's potential for voids, loose zones. You know, your dam is a engineered embankment structure, and now you're putting a loose soil in there. You're interjecting a potential failure mode, right? Those packing in cuttings, they settle out. It's not acceptable methodologies. We see this quite often. You're walking on a small pond, let's say, inspecting it, and you say, well, they must have been drilling there because there's an 8-inch diameter hole that's 2 feet deep, because they packed the cuttings in and they didn't really come back ever to make sure it cleared out and was sealed properly. So grouting using the TREMI method, that's from the bottom up, with a high solid bentonite or cement bentonite grout, is the appropriate method for completing a borehole, unless you're putting some kind of instrumentation in there. But when you're doing that, realize that grout's a fluid, so you introduce the risk of hydraulic fracturing. So be aware of your borehole volume versus your grout take. If you're putting in twice as much grout as you should theoretically based on the size of your borehole, something's going wrong. If you penetrate a filter zone, you can also TREMI place a clean sand and gravel to kind of repair that damage. And I believe we've had 1 or 2 case histories here in Maryland where a driller used a biodegradable drilling mud, sometimes known as revert, to help make that grout, that sealing grout. And of course, biodegradable drilling mud is biodegradable, and that borehole seal just never took. So be aware of accidentally using that or thinking that'll be acceptable. It's so important to maintain logs of your completion details, especially when there's instrumentation, so we can refer back to how this all was constructed. And again, hydraulic fracturing can happen with grouting, so take it slow, maybe fill in stages. All right, another hazard mitigation strategy, and we're all getting down to the end of those, is to prepare for emergencies. So if you're in a high or significant hazard dam, make sure that EAP is updated and on site, okay? Whether you're not in any kind of dam, monitor your dam during drilling. Check instrumentation if it's available. Walk the embankment, the beginning and ends of shifts. Are there cracks, slumping, sloughing, seepage, any of those defects that you hadn't seen before, and think, could that have been caused by the drilling? And make sure there's a plan and materials in place in the event of an emergency, right? You might need sandbags and aggregates to control seepage, or packers to isolate zones in the embankment. And it's not good enough to say, well, we have a plan, we'll call up so-and-so aggregate company. But if you're not knowing how you're going to pay for it, how far away they are they even available, are they open that day? You know, you can't rely on the good nature of somebody to come to your rescue, you know, particularly if it takes a few hours for them to arrive with what you need. It could be too late. Lastly, particularly in a higher significant hazard embankment dam, if you're drilling through it and you think there's some risk involved, consider notifying your local emergency agencies, just for situational awareness. Hey, we're doing this activity. We think we've got it all mitigated, should be safe, but you know, this is where we are. So if we call you, it's probably a big problem. And then of course, once you're done, let them know that you're finished and everything went fine. Documenting those planning efforts is, you know, all part of this. So that subsurface investigation plan that we're going to want to see as part of your drilling permit should be prepared. It helps just provide the train of thought that was went into the planning the process, and it should be reviewed by those folks on site so that they know what the plan is for action. And the investigation plan should be scalable to the hazard class and the extent of the investigation. Again, we're not asking for something that adds huge costs and time to your project. This can really be almost a derivation of your scope of work that you work with your geotechnical engineer to develop. What is in that subsurface investigation plan? Well, the purpose of the activity, the description of what you plan on doing, the methodologies, identify those experienced, qualified drillers and engineers and geologists who will be on site, discuss in some sense the risks you've identified through this work and how you're mitigating them, and then provide an overall schedule of your planned drilling activities. So again, that can be a pretty simple document, but it's really important to have that. Everybody's aware of what the plan for action is. All right, so we've gone through that. We've talked about how to set up an investigation scope, how to identify the hazards and mitigate for them. So what is it that MDE wants to see in a permit application for drilling? And again, we'll be putting this out as a document on our website soon so that you have that available for you. We're going to want to see that subsurface investigation plan, and of course an investigation location plan as well. A table of planned investigation depths and the details. Are you going to finish certain locations with instrumentation or not? If you're going to core rock, how much? What's the purpose of the borings? We're going to look for those completion details. How do you plan to complete them? Are you going to do chummy grouting or something different? The qualifications of your engineers on site, your drillers' qualifications. Of course, an emergency action plan for a high and significant hazard dam. We want to make sure that it's either new or up to date and then you have it. And then, of course, all those typical permitting documents that we would see, like the engineer in charge affidavit. All right, so now I'm getting to the end of here. I will touch briefly back to the first question, so we give you a little bit of a leg up on what we think is often appropriate for how many holes and how deep. First, again, I can't reiterate this enough. An owner or a civil designer who's not a geotechnical engineer should not dictate to your engineer the scope of drilling. You need to rely on the expertise of your geotechnical engineer and make sure you get a geotechnical engineer who has expertise to set the scope that's appropriate for the problems you want to solve, for the hazard conditions of the dam, for the risks that you experience. So that quantity and location of borings does depend on the nature of the project, the size of the dam, and the uncertainty that you need to solve for. So just an example, for a newly constructed dam or small pond, you should absolutely have a boring at the riser location. Many cases we've seen where that's not done, and next thing you know, it's a big change in the field during construction because it's mucky there, and they've got 5 or 6 extra feet of excavation. How are you going to do that? Pouring a thick mud mat, it gets a mess. The riser is a critical element of the structure. You don't want it to settle, so you should know what's beneath it. Also, get something at the plunge pool. Not only does this help you know if you have really erodible or otherwise materials that need to be protected at that location, but it kind of gives you the idea of what's at the beginning and the end of your principal spillway conduit. You should do borings along the center line of your dam and probably no more than 250-foot spacing. But again, that can depend on the uncertainty that you need to solve for. And then you should have something at the auxiliary spillway control section because you want to know, is that, again, a very erodible soil or not? And do we need to design some defensive mechanisms for that? But that's not it, right? So again, depending on the size and scope of your dam, you may want more borings at your abutments or the upstream and downstream toes so you can do proper slope stability and seepage analyses. And let's say you have a very large auxiliary spillway, or maybe a spillway that has very erodible soils, you may want to put a lot more in there so you can actually do a sites analysis and determine if that spillway will be safe for anticipated conditions. So that's, again, the typical locations, and it can go from there. The typical depths we would see for, again, new construction or investigations at existing dams depend on the geologic conditions. Certainly, if you have shallow bedrock, you're going to have shallower depths. But if you do encounter bedrock, we suggest at least a 10-foot rock core, particularly in areas where we have highly weathered rock, or we need to know what that transition is from a soil-like structure to a weathered rock and saprolite down to more competent rock. Your boring depth should extend to an impervious stratum. This is a pet peeve of ours where, particularly in small ponds, it says the impervious core should extend minimum of 4 feet. But what is the minimum? Is it really 4 feet always adequate? Well, no. A small pond impervious core should extend to an impervious stratum. Otherwise, it's like you've got somebody trying to barge into your house and you close the door halfway. They're still going to come in. It's the same with water and seepage flow. If you haven't cut it off completely and closed that door, the seepage can still happen. So you want to extend to an impervious stratum. And of course, this goes without saying. For most geotechnical engineers, it's an obvious statement, is that if you drill to your planned termination depth and you're in soft, loose, unsuitable, junky slop for whatever reason, you keep on going, right? You keep on drilling deeper until you get to good material, because that's going to come into play in one way or another, whether it's because of seepage analysis or settlement or slope stability. You'll want to know about that. So typical boring depths, I think at the riser and plunge pool locations, a depth of about 20 feet below ground surface is probably adequate for a lot of dams and small ponds, but again, may not always be adequate. So consult with your geotechnical engineer. The embankment, the typical rule of thumb is that your drilling depth should extend at least equal to the height of the embankment above it. So let's say you've got a 30-foot high planned brand new dam and you're on the existing ground at the center line, you should drill at least 30 feet below the natural ground. And then at the auxiliary spillway, because we're looking at the erodibility of those soils and the stability of those soils, drill that at least to about the plunge pool elevation or the downstream toe elevation. So we know that if you do an analysis, could you actually breach through that dam and that auxiliary spillway embankment? Hal touched on that yesterday. I believe some examples where that happened in Michigan or Minnesota in the past few years. Something to be aware of. All right, I have successfully gone on for the time allotted, I think. If you have any questions or if there's time for questions, we're happy to answer. Otherwise, we can talk about that later today or reach out with my contact information and we can talk drilling and dirt all day long. Thank you.
John, great
Yes.
presentation. Thank you very much. We have been having some connectivity problems, so there's a couple of suggestions here. If you're using VPN connection, try turning that off, and that may help. Also, if you're still having problems, you might want to turn the Microsoft program off or your computer off and turn it back on again. We have had some success with people doing that. Again, if you've got questions, please enter them into the live event question Q&A block. And we did have one question on EAPs when they're due. They're due the May 1st of every year, and we put a link up there also for our updated EAP model guidance online. And then I believe that there is at least one question. So Jennifer.
Yes, John, you do have one question on drilling. The question is, if we plan to drill a dam which is not under the auspices of MDE dam safety, do we need a permit?
That's a great question. I think traditionally, so let's say this is something that could be reviewed and approved by a soil conservation district. Traditionally, people haven't even sought approvals from the SCD. I think that's a practice that should change, to be quite honest. And the way you look at our laws and regulations, if you propose to alter or change a dam, I would suggest that drilling through it is altering or changing it. You need a permit or approval. So, this is a new, I think, today is the first time some people are hearing about this. So I think it's something that we need to push harder. And as a community, we should all, again, be aware of the risks that drilling in dams poses and the proper methods to do it. So I think we should all be seeking those approvals to make sure that it's documented and we're doing it in a safe and acceptable manner.
Great, so that ends it for the questions. If you do think of something throughout the course of the day on John's presentation, please go ahead and enter it into the Q&A and we'll capture it during the closing remarks. So we're going to take a 5-minute break right now, and we're going to come back at 11 a.m. for Scott Bass with Overtopping Protection 101. Scott, we can see your desktop is live. You want to do a audio check as well?
Yep, hopefully you can hear me.
Good morning, Scott. Loud and clear.
And maybe I will turn on my video for when I get started, and then I'll turn it off as after the introduction slide. Probably best if I unmute, huh? Can everybody hear me okay?
Yes.
Okay. All right. Welcome back to the second presentation of our second day of our Dam Owners Workshop. My name is Scott Bass. I am a water resources engineer with the Dam Safety Division. My specialty is in hydrology and hydraulics, especially dam breach analyses. And today, my presentation is going to be Overtopping Protection 101. First, a brief outline of what I'm going to get into today. First, we're going to get into an introduction to dam overtopping. Let me close out of my mail so you don't hear a dinging. We'll get into modeling considerations, general considerations that aren't associated with modeling, design and construction considerations. And while this isn't a particular slide, I will be sprinkling in the presentation at various points the importance of hiring a qualified and experienced engineer, which has kind of been a theme of the past 2 days of presentations. And then finally, I'll get into overtopping, all the different types of overtopping protection systems. And I will warn you, I have a lot of slides and I will be talking fast, so please bear with me. But first, I want to get into the main reference manual that I've been leaning on for preparing this presentation. And if you are considering overtopping protection, you too should familiarize yourself with this manual. And that is the FEMA Technical Manual, Overtopping Protection for Dams. It has a great introduction for all the general considerations you want to know about before moving forward with overtopping protection, as well as general considerations for all the different types of overtopping protection listed here. I'll also have lots of figures and tables from this manual in this presentation. The second reference I want to make you aware of is the Association of State Dam Safety Official webinars, that's ASDO, of which we are a member. And if you're a paying member, you have access to these webinars. The first is Dam Overtopping Protection Systems Part 1. This is a 2-hour webinar, and it goes into all of the things I'm going to touch on, but in much greater detail. So I encourage you to check these out if you have questions. And the second is Dam Overtopping Protection Systems Part 2, and this goes into more of the testing of all of these overtopping systems that's done at the Colorado State University lab. This is also a two-hour presentation, so in comparison to my 45 minutes, I encourage you to check those two out rather than returning to this one. Okay, so just some basics about dam overtopping, especially for earthen dams, which I'm going to focus on. Earthen embankments typically consist of highly erodible material when subjected to significant flow depths for a sustained period of time. So the basic is an earthen embankment is for holding back water, not for conveying it. That's general principle number one. Many dams were not designed to pass the storm event that they're currently required to pass by regulation. This could be that they're old or hazard creep has affected them, etc. And absent overtopping protection, dams can be assumed to sustain significant damage or fully breach when subjected to significant overtopping flow. And just as a side note, if you've attended our workshops in the past, you'll know that overtopping is the most common failure mode by a wide margin for earthen dams. Some famous examples are the Johnstown dam failure in the late 1800s that killed 2,000 people. And again in Johnstown in the 1970s, there's Laurel Run Dam, there's Tom Sock Dam, which we've gotten into, the famous one in Georgia, the Kelly Barnes Dam failure, which led to a lot of dam safety improvements in the United States. So just know that. One thing we commonly hear is that a good stand of grass will withstand overtopping flows, and this is true. A well-maintained vegetation on uniform slopes with no irregularities can provide some protection during overtopping, but I want to emphasize that this should not be relied upon. Additionally, sometimes we'll have asphalt pathways or concrete pathways on top of the dam or roadways, and this does provide some level of overtopping protection. What I would suggest is that this gives you a little more time before the dam will breach. It does not protect against breach. So my suggestion to you, if you have an earthen embankment, is if overtopping is imminent or is occurring on an unprotected embankment, assume that it's going to fail and activate your emergency action plan and other procedures. So these slides come from a previous workshop that we put on that Paul Schweiger gave, and these come from the USDA Agricultural Research Service, in particular studies by Daryl Temple. And the first, on the left, there's 3 photographs on top which show the first phase of vegetal erosion, which the vegetation loses its cover. The second stage are the middle photographs. Once that vegetation is gone and flow is concentrated in that area, you'll get downward head cutting. And then finally, the bottom 3 photographs of the 9 show head cutting advancing towards the pool, at which case we're in a lot of trouble. If you move to the right side of the slide, this shows that protrusions into flow, irregularities like fence posts or trees, saplings, will cause turbulence and can exacerbate this process and speed it up. So as a side note to the last slide, that's why you'll get angry reports from us to remove trees and fence posts from dams. So reasons to consider overtopping protection if they aren't obvious. Maybe Maryland Dam Safety has classified your dam as unsafe, hydraulically inadequate in a letter sent to you. This could mean that it doesn't pass the design storm required by regulations. As a reminder, low hazard dams are required to pass the 100-year storm with freeboard. Significant hazard dams are required to pass half the PMF with freeboard, and high hazard are required to pass the PMF. Why they wouldn't pass these? You might have hazard creep. Design storms have changed since your dam was designed and constructed. Maybe there's been development in the watershed, or let's just say you want to protect the asset that the dam provides, like a large stormwater management pond, say, that costs millions of dollars to construct. Even though it's low hazard, you might want to protect that asset. All right, so a little more background. Many engineers and owners are probably familiar with Pond Code 378. We've touched on this a lot over the past few days. And if you're familiar with Pond Code 378, you'll know that most ponds in the state are designed to the 100-year storm. So we've talked about the PMF. Let's talk about the PMP, and I'll get into these a little later today. But in Maryland, the probable maximum precipitation is between 27 and 28.5 inches of rain in 26 hours. That's an incredible amount of rain. So if we compare this to the 100-year storm, and I used Montgomery County as an example of 8.2 inches in 24 hours, this is what the PMP would look like in 6 hours, 27.5 inches of rain. And for any pond in the state, you can imagine if it was subjected to anything close to the PMP, overtopping would be a concern for you. And it's even greater when we consider a 24-hour storm, which is 35.5 inches. Okay, so your dam is hydraulically inadequate. Does that mean you have to consider overtopping protection? The answer is no. There are some traditional methods that you should probably consider before moving forward with overtopping protection. These include raising the dam, lowering the permanent pool, increasing the spillway capacity by making riser modifications or increasing the capacity of the principal spillway barrels, adding auxiliary spillways, increasing storage volume through excavation, or some combination of these factors. But there may be some times when you aren't able to use these traditional methods, And some of the things that could impact those considerations are upstream flooding. Let's say you have an urban stormwater management pond, or you have a attractive looking fish pond, let's say that doubles as a stormwater management pond. People like to build houses near open water. If you raise the dam, you might subject these upstream property owners to flooding. On a similar note, if you increase the spillway in an urban environment, you might have homes right at the downstream toe of your dam, and you could potentially flood those homes on a more frequent basis. So that might be a reason why you wouldn't upgrade the spillway. Additional constraints could be property or topographical constraints. You just don't have room to raise the dam or grade out the pond. It might just be impractical or be cost prohibitive to dig up the principal spillway and put in a larger pipe. So all these stakeholder considerations need to be taken into account before moving forward with overtopping protection. A note on acceptance: overtopping protection should not be used as a primary spillway, and we'd like to see these systems activate only rarely, so less than the 100 years, or I'm sorry, less frequently than the 100-year storm. Other options should be considered, I've already talked about. And the design has to be appropriate for the hazard classification, the size of the dam, the flow conditions, embankment makeup, etc., which I'm going to get into in a minute. So it wouldn't be appropriate, for instance, to put Gabion mattresses on a 100-foot tall dam. But we'll get into that. Okay, so you've considered all these things, and now you're moving forward with overtopping protection. Let's talk about briefly some of the options that you have. The first would be roller compacted concrete, which looks something like this. You could also cover this in topsoil and grass if this is unattractive to you or your stakeholders. There could be a concrete spillway, and I will note that this has to be properly designed. Articulated concrete blocks or precast concrete blocks, there's a variety of these. Another type of precast concrete block, wedge blocks, we'll get into these. Gabions. What is this called? Reinforced artificial turf. An example would be hydroturf. And riprap, among others. So the way that we would go about approaching which of these systems we want to choose is we have to have a full understanding of the failure modes, and this is why it's important to hire a qualified and experienced engineer, because an understanding of these failure modes will inform the design. Some examples of these, and this slide comes from the ASDA webinar. High velocity flows could remove your system. Maybe you didn't adequately estimate the flows that your overtopping protection system would face. If you have a concrete spillway, you could have cracks, or the joints could be done improperly. You get flow beneath the system that erodes beneath the system. You could trap seepage beneath your system, and then the system faces uplift pressures, etc. So the take home from this slide is that we need to design it in a defensive manner against these failure modes. So if we go to our FEMA manual, table 10.1 has a helpful table to get started on how to select the appropriate system for your dam. And if you look at the third column, there's dam height. You can see all the different systems have a different tolerance for the amount of fall that they can withstand. A unit discharge of a flow rate per linear foot, an overtopping flow depth, shear stress, etc. And if you'll notice, RCC can withstand 20 feet of overtopping, while cable-tied ACBs have been shown in lab to withstand around 4 feet of overtopping. So this is important. And down to Gabions, about 4.5 feet, but you would have a much shorter dam tolerance. So probably most important when designing this is to understand the flow characteristics of overtopping flow. So that begins on the left side of the picture with subcritical flow. This is low velocity, basically your permanent or your pool behind your dam, which transitions through critical depth into supercritical flow on the downstream slope until it reaches the toe, and you'll have a hydraulic jump, and you'll move back to a slower moving flow. All of these areas are critical to be able to classify so you can properly design the overtopping protection. Another area to note is a subatmospheric zone right near the crest. This is typically where erosion would start in an overtopping scenario. So important flow characteristics to be able to determine for the design of the system would be flow depth, flow velocity, shear stress, flow type, that's the supercritical, subcritical, or the hydraulic jump, and the energy grade line for training wall design. So how do we go about determining these values? Well, your qualified engineer would need to select a hydraulic model. You might use a HECRAS 1D model if you have a simple dam overtopping scenario with a constant slope and a pretty gentle sloping toe. Your HECRAS output will give you all these parameters. If you have a complicated spillway or overtopping scenario where the flow might bend left and right, you might consider a 2D flow. I will issue a bit of caution on these. They provide beautiful looking outputs, but most people can make a beautiful output, but you have to look into the model and make sure that it was set up properly to make sure your values are correct. And finally, you could consider 3D hydraulic modeling for very complex dam scenarios. Your engineer should be able to assist you with selecting that, and I recommend consulting with dam safety prior to moving forward with a modeling technique. But outside of the flow, and I will admit as a stormwater management engineer, with that being my background, I didn't always appreciate that we need to consider the geology, the slope stability, this seepage through the dam, and general dam guts when designing these systems. I probably would determine the flow depth, velocity, etc., and kind of overlook these considerations, but these do need to be considered when designing overtopping protection. Other considerations would be aesthetics, and I know that in dam safety that isn't our main concern. We want a robust dam that can pass overtopping flows, but once we get to public meetings, if you have a roller compacted concrete dam in a a highly developed area, there might be pushback on what that's going to look like. So beware of that. There are also economic considerations for the costs of these different overtopping systems. Some of them are proprietary products. Maybe you aren't able to consider those in your bidding process. So I would recommend consulting the FEMA manual that goes into these in a little more depth. Okay, so some preliminary studies, and I promise this will get a little more interesting. We're still setting it up with some background, but preliminary studies, the goal would be to understand the embankment and foundation. So we might consult construction drawings, borings that were done whenever the dam was being designed. Sometimes these don't exist. So you might have to have a geotechnical investigation program set up. I'll get into that in a minute. But the main goal is to understand the conditions of the embankment, foundation, downstream areas, and then set up a program so that we can obtain the proper geotechnical parameters for a slope stability and seepage analysis, to estimate the bearing capacity of the foundation, to assess filter compatibility with our system, predict settlement, etc. So the goals of a subsurface investigation, first I'll refer you to the previous presentation that John gave. It will require a permit if you plan to drill in the embankment, and that's all I'll say on that. But yeah, the goal of these subsurface investigations should be targeted so that we can understand, like I said on the previous slide, all the parameters for slope stability, seepage, foundation bearing capacity, etc. So here's just a graphic example of geologic considerations. Me, the stormwater engineer, I designed the overtopping protection for the flow conditions, but maybe I forget that I need to evaluate the foundation, and lurking below the dam is an unstable foundation that can't bear the increased flow on the downstream slope, leading to settlement, and then our overtopping protection is rendered useless. Slope stability analyses. Your overtopping protection isn't very good if the existing slope or the slope under full loading conditions is unstable, leading to slope failure. So slope stability analyses, these are required for overtopping protection design. So they need to look at three conditions: the slope stability during construction, during normal loading, and during maximum loading conditions. So there's 5 primary steps. You characterize the geometry of the slope and the material boundaries. You evaluate the material properties for each type of material in the embankment and foundation. Third, you evaluate internal and external water pressure and loading or seepage conditions. 4, you input them into a model to analyze the slope stability. And finally, you solve for a factor of safety. And again, you should hire a qualified engineer to perform these analyses, preferably with experience with dams. And this next slide will kind of hammer home what normal loading conditions. So if we have a dam that, and we do borings for the existing seepage condition, remember this is a pervious earthen embankment, and all pervious earthen embankments do have seepage through them. And we slap an impervious downstream liner on this, what we might in fact do is raise the seepage within our embankment. This poses several problems. First, it could increase uplift on this, the overtopping protection, and if your overtopping protection relies on gravity and the weight of the system to resist failure, this obviously would counteract that. And also, if we understand our failure modes, this creates a gradient from the upper edge of the seepage beneath the overtopping protection down to the toe, and we could have flowing water beneath this system, and you could actually erode the embankment beneath this system. So it's not only necessary to understand the seepage conditions, during normal conditions prior to construction, you also have to have a good understanding of what your system will do to seepage so that we can design filters to counteract this process. So from the FEMA manual, the overtopping protection design must be compatible with the seepage conditions resulting from a modification of the embankment dam, like I just showed. Seepage collection and control features are often required in the design of overtopping protection to collect and control seepage through the embankment or foundation under normal reservoir conditions, like I just showed, to limit the uplift that could develop beneath the overtopping protection as a result of flood releases. So that could water could get beneath the system if you have improper tie outs at the upstream edge, or if you have cracking in the system. And you also need to design the filter to collect and control infiltration of water through the cracks and joints in the overtop protection, which I just said. Some other considerations: you want to inspect the guts of the dam. That would include the principal spillway. You can imagine if we are hired to design an overtopping protection system and we leave out an assessment of the embankment, and we forget to inspect the principal spillway, that we could have an already failing or soon to be failing principal spillway that we've now covered up with an expensive overtopping protection system. It would probably be pretty expensive to rip up the overtopping protection system to take care of a principal spillway upgrade if that could have been done before the overtopping protection was added. Similarly, filter diaphragms. So we showed in a previous slide seepage through the embankment. Well, maybe we go into this project knowing that there's a filter diaphragm, and that should collect the seepage and take care of that problem. But what if this dam was built 50 years ago with CMP underdrains? Have those been inspected? What's the condition? If we slap an overtopping protection system over that, and we failed to inspect these drains, we might be faced with a failing system like these shown here from Maryland dams that could adversely impact the assumptions or the stability of the dam and the assumptions that we've made when designing this overtopping protection. So it's best to inspect these prior to designing your overtopping protection. Utilities, we don't like to see these in dams, but they are within some dams. I suggest when designing overtopping protection that you seek to remove these from the dam once and for all, because the same issue is present. We're going to put an overtopping protection system that we might not be able to remove, or it would be costly to remove to repair these systems. And utility companies aren't always careful or when cutting into embankments to install utilities. This is a stormwater management pond in Montgomery County that I was part of, and you can see the spaghetti that the utility company left in the embankment. Okay, finally, we're going to get into some of the systems that you could select. So the most robust system is roller compacted concrete. And so this is a diagram from the FEMA overtopping manual. You see, to prevent flow beneath the system, there's a cutoff at the upstream edge, and there's a filter beneath the system because this is an impermeable cap that you're putting on this pervious earthen embankment. Some benefits of this, like I said, it has the highest flow tolerance. The table I showed previously suggests that this can withstand up to 20 feet of overtopping flow. It's non-proprietary. There's lots of places that can provide the concrete for this. The manual says it has a relative ease of design and construction, but some people might object to that. And then if you do select this, you would want to move out from the FEMA guidance and actually go to the Portland Cement or the Portland Concrete Association's design manual for RCC spillways and overtopping protection. Here's a close-up from FEMA manual of a adequately designed filter drain. Concrete spillways, if you recall, on Tuesday, Hal mentioned that he'd never seen one of these on a dam that hadn't failed in Maryland. That's probably because they were inappropriately designed. Here's one that isn't on an embankment, but this should be adequately designed. And I'll admit, as a young engineer, I was never concerned with concrete spillways, and that's because I didn't have an appreciation for how complex the flow can be when it encounters cracks and offsets and joints. But we'll get into that here in a second. So I guess one of the main problems with these concrete spillways, and if you're driving along 695 around Baltimore, I guess anywhere in the DC metropolitan area, you'll see concrete channels on hillsides beneath bridges, and a lot of them are undermined. And I suspect what is causing that is flow coming down the spillway in this direction, and it's encountering an offset. If you know anything about flowing water, you'll know that there's a conservation of energy, and if we look at the Bernoulli equation, there's that energy in water has a head component, a velocity component, and a pressure component. So if our velocity component goes to 0 at this offset, we have high velocity water that slams into this offset, the velocity goes to 0, that energy can be converted to pressure, and it'll actually squeeze water between those joints, putting water beneath the system. If it flows beneath that system and you don't have adequately sized underdrains, it could erode beneath the system, leading to collapse of the concrete spillway. Similarly, if the spillway is not designed and constructed properly to account for cracking, you could have offsets and flow irregularities that lead to stagnation pressure and infiltration of water beneath the system, leading to collapse, just like the first offset joint example I showed. And here's an example of a dam in Maryland where I suspect this is the case. First, this is inappropriate because this was designed as a principal spillway. This should not be used as a principal spillway, only emergencies. Second, I suspect the joints were not constructed correctly. Note, I'm guessing the trees didn't help this spillway, but I suspect that cracking and improperly designed joints led to infiltration, which flowed beneath the system, leading to erosion, which eventually led to the collapse. And once it starts to collapse, the process then speeds up considerably. Quickly, just to touch on an example, if you go to the forensic report for the Oroville spillway, they highlight the inappropriate design of the spillway. There's these herringbone drains, they call that, protrude into the concrete that led to cracking everywhere the herringbone drains were. You'll note that the joint does not have a water stop and only one layer of reinforcing. So water had ample opportunity to flow beneath the system through the cracking at the herringbone drains and also at the joints. And if you remember, that led to a football field size opening, which then led to a perhaps billion-dollar disaster. And the main point I wanted to bring up with Oroville is, if you read the forensic report, they highlight the need to hire an engineer, like I've been harping on. So the engineer was hired directly from university with 1 or 2 years as a summer intern at a engineering firm, had no prior experience designing spillways, but had coursework on it. So he was using his coursework notes to design this spillway. And of course, this is still the tallest dam in the United States, and it was at the time it was constructed. But the fact that they didn't hire a qualified and experienced engineer led to this enormous disaster. One other thing that the report shows is that the geologic considerations weren't carried through into constructions. They were kind of lost in the process. This spillway was built on a highly erodible foundation of highly weathered rock. But if you've been around stormwater management facilities and the design of them long enough, you'll know that there's sometimes an assumption that cutting a spillway into undisturbed earth means that it can convey flow, which is, of course, is not the case, but that's a topic for another workshop. So here is an updated state-of-the-art spillway joint. You'll see it has 2 layers of reinforcing to control cracking and maintain its integrity. There's reinforcing continuous across the joint to keep them from separated. There's a water stop in there to, if flow gets in here, it's not going to get past the water stop. It's got adequate drains, and in some cases you might want to provide foam insulation around that to prevent it from freezing. There's a filter material to keep these from clogging, etc. So your experienced engineer will have a good idea about this detail if they're designing a concrete spillway. Some other considerations are cavitation, which we don't have time to get into today, but basically unaerated flow at high velocities when it encounters offsets. It tries to separate from the concrete, but there's no air to fill that void, so it has subatmospheric pressures, and then when it collapses, it can really damage the concrete. Moving on to precast concrete blocks. I will note that these are typically proprietary systems, so if you design these and put or approved equal on the plans, we would want to make sure that the approved equal has been tested at the Colorado State lab or an equal lab, and that the design is appropriate for that particular product. But there's a bunch of different kinds of blocks. There's cable tied, interlocking, overlapping, butt jointed, and here's 2 design guidance documents that your engineer would want to consult if they're moving forward with precast concrete blocks. So the general way these are configured, first we need to have an understanding of the potential failure modes. This comes right from the FEMA manual. The first of which is the shear forces from the flowing water could remove these the articulated blocks from the embankment. So we want to put a trench at the upstream toe with unerodible backfill, usually concrete, to kind of lock it into place. The second potential failure mode are uplift forces. So we want an adequate drainage layer both for seepage flow through the embankment and flow that goes through these concrete blocks. We want it to be separated by geotextile. This is critical to the design. I'll note the drainage layer is also, in addition to conveying seepage flows, it's also makes it more constructible to lay these concrete blocks on a gravel surface. But the geotextile is non-woven, typically needle punched. And then to prevent this geotextile from clogging, we sometimes need a filter layer. We want to know if all these materials are filter compatible, which we'll know through our geotechnical investigations. But that's the general layout of articulated concrete blocks. I will note that the cable tied blocks, typically the weight of the block resists, is critical to the stability of the system. And that'll make sense when I get to another example. So here's an example from the FEMA manual. It's brought in they're cable tied, so you bring it in with a crane, you lay it down. You need details to tie them together. Here's the trench on the top of the embankment. And they chose with this system, if aesthetics are a concern, to cover it with topsoil and grass. It's just a little more attractive, they thought. So some design limitations. You want to avoid complex turbulent flow conditions, especially a hydraulic jump. So your engineer will want to tie it out at the toe at the appropriate location to avoid that hydraulic jump. It should be installed exactly as tested at the Colorado State Laboratory. You'll want to use manufacturer's recommendations for that. And here's an example from the ASDO dam overtopping webinar of what it looks like to tie out the toe concrete with a tie down in a trench. Wedge blocks. So these are also a precast concrete block, and I brought up in the last example the weight of the blocks because this particular system does not rely on the weight of the blocks to maintain its stability. It actually relies on the flow on the downstream edge of these interlocking blocks to keep it in place. It resists uplift pressures through these relief holes. What else about these? An interesting fact about these is they actually can withstand a deeper depth of flow. They can be up for a taller dam than cable-tied ACBs, withstand a higher velocity. I will note these are patented by the USBR, I believe. And so if you want to consider this type of block, Here are 2 design guidances. Again, the webinars go into much greater detail about these, and I can recommend consulting the FEMA manual as well. Here's an example. So I mentioned earlier the use of 1D, 2D, and 3D models. They actually use the lab model to help with the construction of these. That may not be in your budget. But basically, they're just precast concrete blocks. They're not big. These ones actually have holes in them, so it looks like they would be cable tied, but they were corded together kind of to resist vandalism rather than it being necessary to keep them in place. Here's a picture of the filter being constructed. They had several layers of the filter to comply with the filter compatibility requirements. They install the blocks one by one, and they overlap. They appropriately designed the training walls and the concrete cap at the top. And then here is it flowing, and these perform very well. They've been proven in the lab and in practice, so you may want to consider those. A more common one that stormwater engineers are probably familiar with are gabions. These use galvanized wire baskets and are filled with stone. These are typically acceptable on low hazard dams, and they can't be very tall. And of course, this is these are large stones, so this wouldn't be filter compatible with your underlying soils. You would need to design an adequate filter to keep this from failure. And as failure does usually occur when there's not an adequate filter and through foundation failure. Here's an example of a dam in Maryland on an emergency spillway that uses gabion baskets, and it's performed for several decades nicely. The final example is synthetic turf revetments. One particular product, this is a proprietary product called HydroTurf. The benefit of this is it's a high, or I'll get into that later, but it kind of looks like grass, so it's aesthetically appealing. And I'll get into what exactly it is, but I just wanted to show some pictures of it. These were provided by a Watershed Geo who manufactures the product. And they have been tested, and they've shown to perform both in the field and in the laboratory. So what this is, it's a synthetic turf underlain by a structured geomembrane that helps transmit seepage flows. And then the synthetic turf is infilled with this 5,000 PSI concrete binder. And the geomembrane is laid out on the embankment. It's welded together. You put the turf down, and then you sprinkle on the concrete binder, and then you hydrate it. So the construction of this is really important. You'll want either someone that's done it before, or you'll want to consult with the manufacturer prior to selecting a contractor. Another note, you can get this in all different kinds of colors for the turf. So if your dam's already brown to begin with, you could get a brown grass. And this just shows that it was tested and approved for use in the FEMA manual, and it was tested at the CSU laboratory. It didn't fail. They gave the maximum depth of flow on it. It couldn't fail. They dropped, I believe, concrete blocks on it. It still didn't fail. So I recommend consulting the tests if you're considering this. So takeaways before I wrap up. Again, hire an experienced qualified engineer. This is a specialty area of design. You don't want your dam to overtop, but if it does, you want a qualified engineer to design your overtopping protection system. Pay attention to manufacturer specifications and the lab testing data. The lab testing data is only good for what they tested. If you divert from their specifications, you want to justify that to us, because we want to ensure that the system's going to work. And finally, modifications of a dam in Maryland require a permit from dam safety. This includes drilling, but we've hammered that home enough. And with that, I'm at the end of my slideshow, and I'll take any questions. Sorry, that was really fast.
But you're right on time, Scott. Really good presentation. Thank you. We do have 5 minutes for questions. And I believe there's a couple, Jennifer.
Yeah, and Ray, you're echoing. I'm not sure why. There is one question, Scott, for you on overtopping. The question is, any recommendations to minimize turbulence around guardrail posts when they're, any recommendations to minimize turbulence around guardrail posts when there is overtopping of the dam that has a road crossing?
So there was a slide where so assuming that you have an overtopping protection system, you could embed the, you couldn't avoid the turbulence, but you could embed the posts of the guardrail within the trench at the top of the embankment that kind of holds the overtopping protection system in place. But yeah, your engineer would want to consider that when they design it.
Okay, thank you. I don't see any other questions for Scott at this time.
Okay, voice check, testing 1, 2, 3.
That's better.
Great. Okay, so we're going to take a 5-minute break. We will come back at 12. We're going to come back at 11:52, and that will be with Charlie Wallace. He's going to go over Construction 101.
Ray, is everything coming clear?
Charlie, your desktop is being presented live, and your voice sounds good.
The presentation or the speaker's desktop?
Your presentation looks good, Charlie.
Okay, thanks. Good morning, everyone. I'm Charlie Wallace, an engineer in the Dam Safety Permits Division. As engineers, designers, and plan reviewers, we can become pigeonholed in our respective jobs and develop blinders to what happens in the field. This presentation is an introduction to construction. Now, previously we had a workshop called What's in Your Pond, and a similar version of this presentation was made where we focused on 378 pond and dam construction. This presentation now is modified to reflect the other aspects of dam safety. As an owner of a dam, unlike a car, there are no lemon laws for dams. The legal principle, let the buyer beware, or cavat emptor, applies. Now, you need to build a dam or repair a dam, and you might be a private owner, you might be a developer who's has to do stormwater management, transfer ownership to a homeowners association or local government. You might be a government agency, say you're doing water supply or flood control. You could also be a business or commercial entity. How do you go about building a dam? Well, for one thing, you're going to need a permit from the Dam Safety Division. In this workshop, up until now, we have discussed what is involved in getting a permit. John went over permitting 101 on Tuesday. We've discussed engineering investigations and design considerations. What is next now that you have a permit? Are you over the hump? Is everything now downhill, easy street, a piece of cake? You can't just walk into a store and buy a dam like walking into a bakery and buying a cake. There's a recipe to follow. A master baker is needed to get the correct ingredients, mix them in the proper order, and monitor the baking to ensure the cake comes out just right. Just like there are different size cakes, cupcakes, short sheet cakes, wedding cakes, there are different size dams. With increasing size comes increasing complexity. Pond 378 dams employ basic construction techniques, while significant and high hazard dams employ more complex practices and require heightened attention. Today, we're going to talk about several aspects of construction. And first of all, we're going to talk briefly about contracts. This is the legal framework or the platform under which construction takes place. The ground rules are set here, and the engineer in charge has an important role in the contract. Then we're going to talk about construction basics, construction 101, if you will, typical earthwork, spillway, and concrete type practices, as well as specialty construction. Then we're going to look at how dam safety permits apply to construction, and not just new construction, but we're also talking about repairs and emergencies. And we'll go over some of the typical requirements that the permit makes during construction. We'll look at emergency construction and also maintenance and repairs. And we'll end by emphasizing the obligations of the engineer in charge when it comes to their permit obligations. So to begin with contracts. To build or work a dam, if you're the owner of a dam, you're going to have to enter into two principal contracts. And the first one's going to be with an engineer. And then secondly, you're going to have to enter into a contract with a builder to construct the project. Now for the engineer, they've got a lot to do. They've not only got to design the plan, but then they've got to prepare contract documents, which would be the plan, specifications, and then State Highway uses the term special provisions, which is really the contract between the owner and the builder. The engineer also has to obtain permits, has to administer bidding, manage and inspect construction, prepare as-built, and certify the construction to the owner and permitting agencies. And then, of course, the contractor does the actual work. He obtains the materials, supplies the manpower and equipment, and performs the work. Now, as being an owner, I have certain needs. I have a schedule. I may need this dam to be completed by a certain date so that I can do other aspects of a related project. I certainly need the cost controls. I don't want to spend more than I have to, but I want a good quality project. I don't want a lemon. I also have a certain amount of liability. This dam is impounding water, and if it fails, it could hurt or injure somebody or cause property damage. So I really want this to be well thought out and well constructed and have the latest technology. And I also need to manage risk. Anytime you undertake construction, there's no guarantee that everything is going to go as been planned. Now, the engineer in charge, and again, we're hammering this home throughout the workshop. In the dam safety permits, we actually identify this individual in the permit. We refer to them as the engineer in charge, and their PE number and name is listed. and it's desirable that they have experience in dam design and construction. The engineer in charge needs to be the same person in the field who did the design in the office. They understand what was involved in the design and can look for any inconsistencies or deviations from what was intended. And this needs to be one individual. You can have a team that supports the engineer in charge, but there needs to be one point of contact. You're going to have tens to hundreds of people working on a project and unknown large quantities of materials being delivered and handled. This is a very complex process, and there needs to be one person directing it all. Now, if you have a well-prepared contract, the engineer in charge will have the ability to adjust construction as needed to ensure that the design objectives are achieved. And then finally, the work needs to be inspected, and this inspection should be under the direction of the EIC and not the contractor, so that you don't have conflicts of interest. The engineer in charge needs to have control. Oops, I think. Now, cost control can be achieved in contract documents. If there's conflicts in the contract documents, that's going to result in increased costs and delays. And one of the things you can do is establish a priority order of the documents, and usually the plans come first and then the specifications. There needs to be provision to go to the engineer in charge, and they need to be the final authority to resolve issues. The contract also ought to describe what's going to be done if hidden conditions or obstacles are encountered. And one primary way of doing that is through contingency items. You can anticipate certain things that may happen. The soil may be different than expected. There may be something buried in the soil, a number of things that you could anticipate. And if you put this in the original contract when it's put out the bid and you get a price from the contractor, then work can proceed seamlessly at the direction of the engineer in charge. And here's an important point I want to bring out. Permits should be a part of the contract or reference alerting contractors to conditions they must adhere to, but the permits are not contract. If there's a violation of the permit, it can cost time and money, and there's no excuses accepted in this. As has been talked about earlier, a change in scope. Now, the change of scope is with the contract. You don't have a scope with the permit. The permit sets out this is what needs to be done. Again, if it's not spelled out in the contract, it's likely going to cost time and money. Two objects cannot occupy the same place at the same time. I used to do plan review for state highway administration projects for erosion and sediment control and stormwater management. And one primary example that stands out is constructing a bridge. Usually the bridge is crossing a low point of some type. Typically it's over a stream or waterway, and drainage comes down to this bridge from all directions. And the people that are designing the bridge are not concerned about the erosion sediment control. They have to do a large excavation to put in the foundation and drive piles and supports and the like. Whereas the person that's doing the erosion and sediment control may not be aware of what is happening with this foundation or intermediate type construction. And so they direct everything to this bridge and put a sediment trap where the bridge abutment's going to be. So when plans are being prepared, there's certainly a specialization in discipline, and one discipline may not be aware of what the other is doing. And it's important for the EIC to be alert to this and try to monitor plan development and look for these types of conflicts. Now, there also can be site constraints, and for the contractor, where they make their money and they have their area of expertise, is they get the job done. They know how to do it. But when you're doing plans like in a subdivision, a lot of times stormwater management dam gets pushed to the remote area of the project that's not really usable to sell as a lot, and access and other types of constraints can happen. Also, utility lines are often depicted on plans as just a single thin line, whereas if they're deep, you could have a very wide excavation to accomplish the work. As we talked about substructures, foundations, these may not be seen on the final proposed grades. There's intermediate grading that goes on, and this needs to be considered. It's important to size your trenches to accommodate standard equipment. Otherwise, you may be getting into hand work and hand shoveling. Talked about access of equipment, and then groundwater. It's important to do work in the dry, and sometimes wells and pumps and different things need to be provided in order to do the work properly. Now, in my opinion, the inspector has the hardest job in the whole construction process. Usually they have the least formal education, but they're expected to know the plans and specifications, and usually these reference national and proprietary specs. They need to know the permit conditions, and then they need to understand the contractor's means and methods. They need to know how the contractor is going to tackle the job, what means of egress he's going to have, where he's going to work. But they also have to be prepared to turn on a dime, so to speak. The contractor may have planned to work in an area, and then overnight there's rain and he can't work there, so he moves his work equipment to another location. This isn't to try to trick the inspector, but rather it's to keep the project moving along and to keep people working. And very importantly is, if the work is inadequate or unacceptable or failing, the inspector has to speak up immediately. If you don't, then, especially like if you're doing the fill construction of an embankment, the work will just be covered over. It's important to remember that an inspector cannot supervise a contractor. They can only accept or reject the work that's being done. Now, if the contractor isn't doing acceptable work, you're not slowing the contractor down. You're telling them they're not doing acceptable work. But you also want to be careful not to direct them how to do their job, or otherwise you could be accused of that. The inspector is often referred to as the eyes and ears of the engineer and needs to know when to get to the engineer. Now let's get into actual construction activities. This is where the virtual plans become the reality. The actual dam is constructed. There's common types of activities, and then there's also areas of specialization. And we'll start with stakeout. And I want to illustrate something here. This is a straw bale dike detail. It's not commonly used anymore, yet on the plans, the symbol for it is a dashed line, as you can see in the upper left-hand corner. However, not everybody knows how to read plans. And in this case here, rather than having a continuous line of straw bales to intercept and filter water, sediment-laden water, you have a dashed line just as it was symbolized on the plan, even though the symbol isn't what was expected to be constructed. And stakeout is one of the initial things that's done on a project, and you have both vertical and horizontal control to consider. The stakes are usually offset so that the equipment can work without interrupting or destroying their benchmarks. Earthwork sites can be very busy. You can have a lot of equipment moving, a lot of materials being placed, a lot of people active doing things. One of the common things with dam construction is there's excavation. You have the original ground, and then we have what's indicated as a construction subgrade. Sometimes once you get to construction subgrade, the soils aren't stable and they need to be replaced, and this extra excavation is referred to as an undercut. And what we're looking for in the construction subgrade surface is to have stability, and we don't want pumping. And if you can get equipment on there, you can see how the soil behaves under it, and that's known as proof rolling. And if you can't do that, the inspector can just walk with their heels or their feet and push in, and you get an idea how stability is going. Now, sometimes undercutting isn't limited to just the soft areas. You want to have a uniform surface in some cases, where if you're going to be supporting a spillway, or you don't want to have uneven settlement, so you want to make sure that you have a uniform surface that is going to support the construction that's about to follow. Here's a photograph where the cutoff trench has been excavated, and they're starting with the first lift of backfill of clay material. You can see in the background that there's a sheep's foot roller that's being used to compact clay. That's the proper equipment for kneading the clay material together to try to make it more impervious. And the construction is stopped while a compaction test is being taken. The individuals bent over using a nuclear gauge. Now, in soils, we usually classify them in three ways: sand, silts, and clays. Sands are larger particles. They don't really stick together well. They're called cohesionless. And on the opposite end, the most finest materials are called clays, and they're cohesive. They stick together, and moisture is very important for them. And then intermediate sized particles are referred to as silts, and these tend to get muddy and slippery when getting water introduced, and they're not the most desirable materials to use. When material is going to be backfilled into an excavation, the material you're placing in there has been fluffed. It's not going to be as dense as when it was excavated originally, so a compaction effort is needed. And there's standardized tests referred to as Proctor tests to test this compaction effort. And originally, when compaction was being tested, the standard Proctor was developed, and that's a measure of the expected density of the material in pounds per cubic feet at a given moisture in the backfill. However, over time, compaction efforts have gotten better, and you get strong, higher density. So a modified Proctor was developed to reflect the current standards. With dam safety, we prefer to have standard Proctors used because it usually results in a higher optimum moisture content. It's important to remember that soils are not man-made like concrete and aggregates where you have control of their properties. Their soils are subject to considerable variability in their characteristics, and you need to have an experienced inspector so that he can watch the and he needs to be present to watch the performance of the soil under compaction equipment, and he needs to understand and select the proper soils Proctor curve to do the testing. Again, optimum moisture content affects the ability to compact the soil, the lift thickness. The thinner the thickness of the lift, the better compaction effort is going to be. And finally, the compaction effort itself is the number of passes and the weight of the material, the roller on the soil. Standard compaction testing methods used to include sand cones. You don't see them much anymore, and it's now the nuclear density gauges. The gauges are portable and they give you fast answers. Now here's a photograph of an individual performing a Proctor in the lab, so to speak. You have a mold, and you start out by putting dry soil in the mold and lifts. And with each lift, the compaction effort is simulated by this hammer. The individual has lifted a weight and will release the weight, and it'll fall a given distance and impact the soil. After this is done the given number of times, the soil is weighed, and the moisture content is determined, and then the soil is remixed with water added at a higher moisture rate, and the test is repeated. And you do this 3 to 5 times, and you'll develop a Proctor curve showing density on the y-axis and increasing moisture on the x-axis. And we can draw a smooth curve and determine what the optimum moisture is, and we can try to usually specify that the placement of the soil should be within a given percentage of this optimum moisture content. Different materials have different dry densities, and moisture affects them differently. You can see that clays are more moisture sensitive and require more moisture, while crushed stone and sand are not very moisture dependent, but they do get higher densities. And here's a photograph that, again, a sheep's foot roller has been used and a compaction test is being performed in the field to determine the in-place density. In this photograph, there's a more sandy type material that is being used, and there's a smooth steel drum roller that vibrates, and this is more suited for compacting cohesionless material like sand. If you're working in an existing embankment and you have to excavate into it, you need to key your excavation back into the existing dam so that when you refill it, you don't create a slippage plane as you would if you just create a bucket excavated trench. This needs the backfill back into the existing dam. You don't always have soil. Sometimes you encounter rock. Here's an example of an excavator breaking up the rock before it can be removed. Sometimes you have to perform excavations at the toe of a dam or somewhere in its close vicinity, and so supportive excavation is needed. You may need to temporarily hold the dam up while you're doing the work. And here's a photograph where sheet piling is being used. In some cases, more elaborate supportive excavation is needed. In this case, there's an open air reservoir that's active, and excavation that's shown on the left, and on the right is the area where excavation needs to take place. So a secant wall is being constructed here, where you auger holes into the ground and fill them with concrete, and you build a concrete retaining wall prior to doing the excavation. And here's a photograph of that same site. You can see the full reservoir, but before they did the excavation, this concrete secant wall is holding the dam and excavation up in place while the work continues and progresses. And yet this is another view of it showing you how deep the excavation was. There's other types of supports of excavation too. We have gunite supported walls, there's soil nails, there's a variety of things that can be done also that the work can perform safely. We've talked about working in the dry, and a lot of times dams are built in the run of the river, so to speak, and so there's a large drainage area coming to the dam, and sometimes very elaborate diversion works are needed to divert off-site water around the dam so that you can perform the work as needed. And here's a photograph of a cofferdam that with sheet piles you can remove them, but in this case it was going to remain in place. On the left is the active reservoir, and on the right is the area where the reservoir is being separated out. It's going to be dewatered, and construction is going to take place in that area. Here's a sheet pile cofferdam, and you can see how effective they can be at holding back a body of water. So this is a good technique that a contractor can use. And here's a not so good technique: plywood and 2x4s to divert flow around a construction site. Sometimes it works, sometimes it doesn't. Sometimes it's safe, sometimes it's not. Spillways are integral parts of dams, and usually you have principal spillways and auxiliary or emergency spillways. And with both of these, we want to talk first of all about they need to be placed on natural ground. And when a contractor is building something, he has a grade that he's shooting to construct, and maybe the grade stake isn't set right, or the excavator gets a little over ambitious and he over excavates an area. With the support for the spillway pipe or in an emergency spillway, we want it to be on natural virgin ground. We don't want this over excavation, and it's important for the engineer to monitor what the contractor is doing closely in these situations. And if a problem does arise, you may need to stop construction and consult with the engineer to determine how to proceed. You can't just put fill back as you normally would in other sections of the dam. Spillways are typically constructed offline in the dry, and then once the new spillway is constructed, then the flow is directed back to the new spillway while the remainder of the dam is constructed. And here's a photograph showing concrete ASTM 361 pipe being placed and the concrete cradle coming up to the spring line of the pipe. And again, note that it's all being placed on natural soil. Here's another photograph of a spillway pipe, and you can see that the impervious core is being brought up with the spillway pipe. It cuts at a 90-degree angle across it, and it's shown that the clay is a reddish type material. We want to bring both the spillway and the impervious core up at the same time. We don't want to construct the embankment and then cut in a trench to put the pipe in. The section of the pipe should be clear. There shouldn't be any separation of the joints. There shouldn't be any deflection or depressions of the joints. And we're going to talk a bit about concrete. And why this requires special attention is a lot of money and effort is spent in this. And so it bears at least understanding of what's involved. And the ingredients of concrete are cement and water, which mix to make a paste, and then they bind fine and coarse aggregate together. Air entrainment is often used, and I recommend it highly because it really increases the durability of concrete with very little effect on compressive strength. It also assists in making the placement a little easier, and there are numerous admixtures that can be placed in concrete to accelerate set time, to retard set time, to assist in pumping, to add the attainment of strength. And the cements, there's 5 different types that are commercially available. Also, sometimes pozzolans like fly ash are added to the mixture to cut the cost down a little, but they also behave in a cementatious matter. When concrete is mixed, it can be either be mixed at a plant or in the truck. And it can either be mixed wet or dry. And a lot of times, the site where the concrete has to be delivered is remote, you mix it dry and then add water once you get to the site. It's important to timestamp the ticket once water is introduced to the mix, because within about 2.5 hours, you're typically going to have initial set. Once you add the mixing water and the concrete mixes, after about 10 or 15 minutes, you want to stop adding water, because that's referred to as tempering, and that can have a negative effect on strength. And again, we talked about there's plenty of admixtures that can be placed in the concrete. When concrete's delivered and placed, there's common concrete test, the slump test, the air test, and there's 2 different devices for that. We want to check the temperature. Concrete can get quite hot, and we also don't want it to freeze. The unit weight's important, especially if we're looking at any flotation of risers, and cylinders are usually cast and broken at 7 and 28 days for compressive strength. Here's a photograph of an individual performing a slump test. The mold is placed in the other direction and added in a prescribed manner, and then the mold is lifted off and the concrete slumps over, and the amount in inches that this concrete slumps is measured. Here's an example of somebody running a pressure test on the concrete. I mean, pressure, using a pressure meter to check the air entrainment. And when you're placing concrete, you don't want it to evaporate and set too quickly. You want it to cure slowly. So a lot of times plastic is placed over the concrete to control this, or a chemical admixture can be sprayed on, a curing compound can be sprayed on the concrete. And again, if it's in cold weather, you may need to put blankets over the concrete. Once it has initial set, you may even need to make provisions to heat the concrete. And in the summertime, ice may need to be added to the concrete to keep it cool. Also, it's not always practical to back a truck up to where the concrete needs to be placed. So pumper trucks like the one shown in this picture can be used to move the concrete from the truck to where it needs to be placed. And it's important to vibrate the concrete when you're placing it in the forms, especially if there's reinforcing steel. And you can see it's usually a 2-man operation, one individual holding the power source and then the other one placing the rod in the concrete to distribute it evenly. Segregation can also be a problem when you're transporting concrete. The stone can settle to one side and the paste can separate from it. And minimizing the distance that concrete is dropped from the chute helps to prevent and minimize segregation. In this case, extension chutes are added to the concrete mixer to get the concrete actually closer where it needs to be placed in the buckets to be delivered out to an offshore site. And we've talked about roller compacted concrete. Scott brought this up. And here you're taking typical concrete, and rather than setting it in forms of reinforcing steel, you're placing it as if it was a soil, and you're compacting it like it was soil. For economy of scale, usually you can set a batch plant up right next to where the dam is, and you can have the cement brought in and have the aggregate stockpiled like you see in this picture, and it's mixed in the bin there. And in this case, you're actually able to place it on a conveyor belt and move it right to the site where the concrete is needed. You can also batch it into dump trucks, and then again, it's a short drive to drop it where it needs to be placed. And this is a quick and cost-effective way of placing concrete for a dam. And you can see a picture here. The roller is actually going over the concrete once it's been placed. And again, you monitor the lift thickness, and it can also be compacted tight against a spillway like you see in the foreground here. There are certain properties of finished concrete that we don't like to see, like pop outs, spalling, cracks, honeycombs, and cold joints. And with cold joints, the problem arises there is if you have a large pour and there's an interruption in the pour, say normally you'd like to have the trucks coming in a uniform and consistent manner, and as soon as one truck empties, the next one's ready to take its place and continue providing concrete. However, if there's a half-hour break in that for some reason, the equipment breaks down, there's a traffic jam, whatever happens, cold joint can form, and it's important to pay extra effort to try to keep the in-place concrete plastic as long as possible so that you can mix the new concrete in with it and not have this cold joint be formed. Reinforcing steel is commonly used in construction these days for concrete. And here's a photograph of a riser being constructed. The forms are being placed inside and outside, and the reinforcing steel is in the middle, and it's coming up in a uniform manner. This is what the inside of the forms would look like. You can see that the cross ties that hold the forms together, and they'll be left in place once the forms are stripped. There's uniform clearance between the reinforcing steel and the forms, and everything's tied together and is very clean and very neat. Bracing is usually needed for forms, especially if you have a large pour. And water stops are very important. And this is an advantage of a cast-in-place product like a riser. The base is poured. You can see the water stop is placed in a strategic manner in between the reinforcing steel. It's embedded into the base. And when the walls start to be poured, it'll make the whole joint watertight. And this also includes going around the pipe that's going to be in place. This is a stub out section of the pipe. All dams leak. We've talked about that. There's a certain amount of seepage that is always going on, and mechanisms to control that are filter diaphragms, toe drains, and other types of filtering processes. Here's a photograph showing a filter diaphragm being constructed simultaneously with the construction of the principal spillway. The sand needs to be held in place briefly by a form such as the plywood that you see on the right-hand side there, and this filter diaphragm extends underneath of the principal spillway. The concrete cradle is yet to be poured. And then when you get to the top, you can see that these filter diaphragms can be pretty large, especially as the pipe gets larger, and compaction is needed for the filter diaphragms as well. You can see the nuclear gauge that's in the middle there that's been testing the filter diaphragm as it's being constructed. There are no springs in dams. I cannot tell you how many times somebody has told us, oh, that there's a spring in the dam, and they didn't think anything of it. If there a spring or water flowing through the embankment would be a sign of seepage. You also look for soft spots if you're walking on the embankment, or you look and see areas where the vegetative growth is doing better in one area than another. These are all areas of potential seepage, and they need to be investigated. And you don't always just look on the dam. You can look downstream of the dam. If you see water moving soil up from the ground, forming what we call boils, that's an indication of seepage underneath of the dam, and that can create a problem. And it's very important when you're doing the first filling to look for these signs of seepage. This is the first time the dam has been subjected to the full water load, and if there's an inconsistency or unconformity, it's liable to show up when you're doing this first forming. You also want to look upstream of the dam and see if there's whirlpools that are forming in the impounded reservoir. That's an indication, again, that the water is being sucked down, and it either could be going into the dam or underneath of the dam. And an interesting little side note is on a lot of dams, once the water has been diverted into the newly constructed spillway, the original water body or stream or river, it usually has slightly different geology than the surrounding ground. And that's an area where seepage will occur, and it needs to be monitored and controlled, but it's not necessarily a problem. And when you stand on the dam, you always look downstream, so that then the left will be on the left-hand side of you and the right on the right. Again, you're looking downstream. And in this illustration, this is a plan view. You showed where the new spillway is constructed first, then you would divert the flow from the stream into the spillway and then continue to construct the rest of the dam. And in hashed lines, you can see where seepage is likely to be seen in the future. And we've talked about emergency spillways. This is a photograph of our articulated concrete block being placed on the suitable filter material underneath. We usually don't like to see large flows and spillways. This was a low hazard small dam that it was unavoidable due to site constraints to avoid having some flows go through the emergency spillway. So it was armored with articulated block in this case. Normally we like to have it on a grass on native ground. Talk about landscaping. This is what we like to see. It's a smooth, clear stand of grass. There's no trees, no woody vegetation, no unusual overgrowth. You can inspect this dam easily. You can see if a sinkhole develops or some other like rodent burrows, different things like that. You can inspect the dam very easily when it's maintained and developed like this. Now let's talk a little bit about specialized construction, and the first one is blasting. We're going to talk later about the fact that usually we don't like blasting and it's prohibited. However, there are occasions that arise where blasting is unavoidable. And if you're working next to an existing high or significant hazard dam, we're going to require activation of the EAP to level 2. This is so that the emergency management people, it's more of a situational awareness where they know what's going on. They get out their emergency action plans. They're prepared if they do have to close streets or evacuate people. They don't have to go frantically searching for things, but they're prepared and ready to act if the need arises. To do blasting, a permit is needed from the state fire marshal, and you need to use an experienced licensed firm, and they always have experienced licensed personnel. A blasting plan will need to be prepared, describing how they're going to conduct their operations. And if you have existing structures around the dam or the dam itself, a lot of times survey monuments need to be placed on these, and they need to be monitored throughout the blasting process. And sometimes there's also extra supportive of the excavation may be needed or surrounding structures. Now, I've put this in. This is our little trip to Hollywood. Here's a case where there was an existing run of the river dam, and it was decided that the way to breach it was to blow out the first section here, and this is about 10 minutes afterwards. Now here's a case where a dam was being breached and the spillway or the stream channel through the breached dam was not stable. So this had to be redesigned. In dam safety, we're not proponents of precast sections. We don't like them, and this is one of the main reasons why usually you don't get them as a monolithic section, just one piece. We have two pieces that have to be joined together, but sometimes circumstances require that that's what we get. And so in those cases, not only do the joints need to be sealed, as you see here, but we do everything we can to make them watertight. There's mastic that's taped around the entire joint, and then there's steel straps that need to be designed to hold both sections together. And also you can see that in this case, the pipe had to be mortared into place rather than being cast in place. And so this is an area where the mortar is likely to deteriorate over time and leakage can occur. Slip lining is another activity that we commonly see these days. If you have an existing corrugated metal pipe and it's starting to deteriorate, its expected life has been exceeded. If it's still structurally sound, you can slip line it. In this case, here's with HDPE pipe, and the point usually comes in sections. They're jointed together and then brought along together with a come along, and they're pushed in by a large piece of equipment. Another type of specialized construction is grouting. and you commonly see this when you've excavated down to construction subgrade, and maybe there's excessive joints or cracking in the rock or bedrock, and you might want to seal these before placing the dam, continuing with the dam construction. Or if you have an existing dam, there may be cracks and seepage through the dam, and this may be one way of controlling the seepage and interrupting it. Jacking and boring. Sometimes there's a road on the dam or other type of activity where it's not practical to do an open cut, and many tunneling excavation activity needs to take place to push a pipe through the a new pipe through the embankment. And we can't emphasize enough too, you need to be conscious of constructability. In this case, the whole site was mass graded and cleared first, but the dam needs to be constructed at the far end of this. And if it's a rainy season like it was here, it's next to impossible to get the materials and equipment to the site to build the dam. Also, large equipment may need to be brought in to economically bring forms and materials down to where they're needed. Now let's talk about permits. This is the end game. We have our permit, and you're the engineer in charge. Now, what's expected of you? Well, common dam safety permit requirements that we have, you see these in most of our permits, are stream closure periods. Almost all dams are built over a stream, and we have 4 different use designations in the state of Maryland, and depending upon what use stream you're in, there's different times of year that you can't work in the stream. Now, you can work outside of the stream, but not in the stream itself. We also require that you notify the Dam Safety Division prior to starting work. We like to arrange a pre-construction meeting just so that we meet everybody and we know the ground rules and that things get off on a good start. And again, we typically prohibit blasting. We'll often require EAP activation if the circumstances require it. We do require progress reports, and we require these weekly. Again, like we talked about with inspection, the sooner we see what's going on, if we see a problem, the sooner we can tell you about it so that it can be economically and quickly addressed rather than becoming a problem that becomes expensive. At the end of a project, before you do the first filling, we require the engineer to give us written notice that the dam is ready for filling, and then we need to authorize that. And we're also going to look for a filling plan so that we know that the dam is being properly monitored during this first filling. And at the end of everything, we require an engineer certification of the construction completion and the submission of as-builts. Now, this is the typical in-stream closure periods. I won't go over these except for use 3, which is always needs to get a permit from dam safety. The closure periods there are between October 1st and April 30th of each year. This is the progress completion of weekly progress. I'm getting tongue-tied here. Weekly construction progress report. We require this to be electronically submitted weekly. It tells us what percentage work has been completed. It's kind of a good record of progress. We have a place for remarks from the engineer in charge as to what is occurring, and we also expect representative photographs to be attached to this report. And then finally, when the project is completed, this is the certification that the engineer in charge needs to submit, and you're certifying that this dam was built according to the plans and specifications that were approved. And both the engineer in charge and the permittee needs to sign this. A lot of times, we're not only constructing new dams, but we're working on older dams. These older dams are not necessarily constructed to current standards. Construction information may be scant or not available at all. A common type of procedure that was used on older dams was puddle cores. It was a real wet, soupy mixture of a clay type material to try to make an impervious core. And the condition of that 50, 100 years later is not guaranteed. It's important. I mean, a lot of these dams are neglected. They've been sitting a long time, and you get excessive growth on the embankment, and this requires removal, and a lot of times that needs to be permitted. We like to encourage non-destructive testing using geophysical methods. As we've been talking about today, borings are sometimes necessary, and you can also do a video and camera inspection of the existing pipes. And you may encounter problems because there could be valves and gates that haven't been operated for years, and they may be bound up and may not work. And here's a photograph showing a jungle that's grown on top of a dam embankment. And this clearly would need a permit from the Dam Safety Division. And all this needs to be removed before you can do an inspection to see what the condition of the dam is. Here's somebody that's running some geophysical testing. It's non-destructive and non-invasive, and it can give good insight into if there's any voids or flowing water underneath the ground. This will detect a lot of that. And sometimes we need to do borings. It's just the way it is. And then this is a drill rig getting ready to do some borings. One advantage to doing borings, though, if you have to do it, is you can also put permanent monitoring wells in place so that you have a continuous read in the future as to what's going on in 20 years, even from now. If there's a dam emergency, the readings from these wells, if they're kept up over time, can give you some valuable insights into how the dam embankment is performing. Talked about doing video inspections of pipes. There's a camera that's mounted on a wheelbase that can be remotely controlled and go through the spillway pipe. And in this particular case, it was a pretty large spillway pipe and a pretty elaborate production. There was a truck that had a monitor and also a computer next to it to track where the camera was, and you could stop the camera and turn it at each joint and look at the condition of the joint and see if there was seepage or other problems that arise. Often it's necessary when you're working on an existing dam that you need to dewater it before you can do the work. And common methods of dewatering include pumps, siphons. Hopefully you have a lake drain, and then there may be spillway valves and gates that can be operated. Here's a photograph of a pump. They're quite large and they're expensive to rent and use, but they do a very good job. And it's not just the pump. You have oftentimes you have a large spillway pipe that's or I should say a discharge pipe that's needed from the pump to move this water away from the dam. However, they can move a lot of water very quickly, and these are useful in an emergency situation. Now, if you're not in an emergency and you've got more time, you could create a siphon where you let gravity do the work. And here's a photograph of a siphon with the T on the top so that you can add water there to prime the siphon. You have existing valves, and many times these valves may require 100 or more turns to open and operate them. And so there's truck-mounted mechanized devices that can do this turning of the valves for you. Here's a valve in particular that hadn't been operated in what was guessed to be over 100 years, so there was no guarantee it was going to work. However, it did work, and after about 5 minutes, clear water was coming out of the downstream end of that lake drain. Now let's talk a little bit about emergency construction. Most people don't think of emergencies as construction, but usually they are. And you don't necessarily have to have a permit if this is an emergency, but we want you to contact us right away and notify us of the emergency and what is going on. We're not out to create problems for you, and we can sort out the legal details and what type of violation or notice is needed down the road, but we want to make sure that nobody gets hurt, and we want to try to help you keep your dam. If you have emergency construction, this is likely going to be expensive. Rarely do you have an emergency during 9 to 5 business hours. Usually it's on a Friday before a holiday weekend. You need to be able to get equipment and materials. You need to have provisions for this in advance. You may need to set up survey monuments to check existing structures for movement. You're going to need engineering support and a contractor. And again, these are all at off hours. You got to prepare for that, and it can be very expensive, and it can also be risky. You could be working in a hurricane. You could have flash floods. You're fearing sudden collapse of the dam or other structures, or even a worker that they could be sucked into a riser. There's a lot of things that could happen. And certainly if we're dealing with an emergency, we're going to expect that an emergency action plan has been activated. There's 3 levels to an emergency action plan. Level 2 is basically we still have the opportunity to save the dam if we take corrective measures. But there comes a point of no return where you can't save the dam, and then you need to get people out of harm's way, and that's what level 3 is. We're trying to save people. And in level 2, we notify the emergency response personnel that there is a situation that is occurring, and they can be prepared so that if we have to go to level 3, they can step into action immediately. Here's a photograph where on the left is an existing reservoir, and you can see the concrete wall at the top of it, and it was active, yet excavation was going on to below it, and the wall started to move. So quickly, gravel and the like was filled in the void between the wall that had been formed and the supporting earth that held the existing reservoir in place. Plus, bracing had to be thrown up to keep to support that wall, to hold it in place until an engineering solution could be developed. Can't emphasize enough that it's important to do routine maintenance because it prevents emergencies. Here's a case where in September of a given year, a routine inspection was performed, and you could see that there was sticks and twigs and beaver cuttings and the like in this riser, and the owner was told to remove these so that a problem didn't develop. 6 months later, in the middle of winter, a problem developed. The flow, you can see it isn't coming out very quickly out of this spillway pipe, and that's because the riser is plugged. On most high hazard and significant hazard dams, we like to have a staff gauge in place. And if you don't have the actual elevations marked, we at least like to see them marked as green, yellow, and red, with green being the pond level is at an acceptable level. If you get into the yellow part of the staff gauge, you're getting into issues and there's problems, and this is where we'd probably be in level 2, where we're still trying to take remedial action to save the dam. But if it gets up to the red in the level 3, then we got to start evacuating people. And in this case, when we get to the red, you would start having flow go over the emergency spillway, and that would flood people downstream. So in cases like this, again, not only do you have to have pumps and the associated piping, but you got to be able to get this equipment to where it is needed on the dam. And the photograph shown here, using a tractor and that in muddy conditions, because again, these always happen in rain events where it's not favorable conditions. They had a tractor to assist getting the equipment where it was needed. Now back to our original example where the riser was plugged. Helicopters were used to deliver 2 large pumps to the dam, and plus the tank to hold the fuel to run these pumps. Talking big bucks doing this type of thing. And it's dangerous. Here's a case where 2 workers with this, they had to go out onto the frozen lake level of the pool and use chainsaws to cut through the ice so that they could put the piping in there to lower the pool down. Now, after a few days, you can see the pool levels come down, and not only is the yellow showing, but if you look closely, you can see the green is starting to emerge at the bottom of this staff gauge. So we're now getting into an acceptable level where people can go in and safely do work to clear the spillway and return the dam to normal operation. This is a Chinese proverb I'm particularly fond of. It says, dig the well before you are thirsty. And this gets to the idea of we need to have a plan in effect of how we're going to deal with an emergency before the emergency happens. And that's why state law now requires the preparation of these emergency action plans for all high and significant hazard dams. And this is a cover page of the required emergency action plan that you can find on our website. And again, among the things that are shown in an emergency action plan is a description of each of these levels. Level 1 being an unusual or slowly occurring event. Maybe you've noticed something during the inspection, some seepage. It raises concern, but it's certainly it's not a rapidly developing situation, and you have time to do an engineering study and come up with a solution. However, if you say you had seepage coming through the dam, and rather than it being clear water, you're now carrying sediment in the water. This is a situation that is happening rapidly, and quick immediate measures are needed to save the dam. And if you're not able to do that, then we go to level 3, where again we have to get people out of the way. And this emergency action plan provides some guidance and direction as to how to approach these emergencies. Maintenance is construction as well. Here's a dam that has a bridge supported, that supports a bridge on top of it. And it's a run of the river dam, and some large tree trunks and other types of woody debris have floated down the river and are collecting along the bridge supports, and it's creating a secondary type weir, and this could unintentionally raise the level of the pool behind the dam, and that's not desirable. And this is a large enough activity that you need to get heavy equipment in there in order to safely remove it. And you also have to have a place to put the material. In this case, once you remove it, you don't want to sit it right along the edge of the river so that when the next flood comes along, it's resuspended and goes back against the dam again. If you have any questions as to whether you need a permit from dam safety or not, contact us, talk with us. We'll give you some guidance as to how to proceed. Our dam safety permits do call out very specific activities for an engineer in charge. And again, the first thing is we mentioned in the project, in the permit, who the engineer in charge is, their name and their PE registration number. We expect the PE to keep a history of the construction activity, to keep a record of testing that's done, compaction tests, concrete tests, and the like. Keep a photographic record of this. And then once the project is completed and the engineer is ready to file with us the project completion report, we expect to get as-built within 60 days of that. We also expect to be notified by the engineer in charge prior to the first filling of the dam. And in some cases, there may be a requirement to maintain a certain minimum base flow through the dam, and that needs to be certified as well. And we can't forget that this doesn't happen in a vacuum. Usually there are surrounding communities and neighborhoods, and if it's a large dollar project, there's certainly political considerations to keep in mind. And you want to try your best to keep negative happenings out of the papers. If you have an angry, upset neighboring community, they can quickly shut down your project or make things very difficult for you. In this case here, we have the Secretary of the Department of the Environment, Ben Grumbles, being interviewed for a TV newscast, and this was favorable press in this case because in-stream dam was being removed, and that was viewed as an environmentally desirable thing to do. And some final thoughts. We want you to, these are like life lessons. You can't assume that people are going to read the permit. We know that firsthand. I can't tell you how many times we come across a situation where if the permit had been followed, we wouldn't have even had to get involved. As an engineer in charge, you can't assume that the contractor is going to follow the plans. They have certain ways that they're used to accomplishing things, and it may work well for a highway, but not necessarily for a dam. We're all creatures of habit. I know as a young inspector, I would have to say to somebody 20 years older than me that you're doing it wrong, and they'll come back and tell you, well, I've done it this way for years, and now you're telling me I'm doing it wrong. And you have to learn to stand your ground and say, well, this is not what's approved, and this is not what you're allowed to do, and push them to do it the correct way. If you're designing the plans, it's important to make it bold, something bold on the plans if it's critical, if it's unique, if it's something that you don't do in the course of normal construction. Also, there's a lot of obvious things that are stated on the plans. Boilerplate, this stuff matters. Usually a regulatory agency may have standard plan notes that they want to see required, or you as the engineer, you may have developed notes over the years that you need to add to the plans because you've had problems and you found a good way to address it. It's important to test and operate any gates and valves or other mechanical equipment that may be installed during the construction. And it's important to remember that when you get close to the end of a project, which is referred to as substantial completion, the contractor is going to want to start to demobilize. He's going to want to start taking his manpower and equipment and move them to another project because he's not making money with them sitting on this project being idle. And before they do that, you need to prepare a punch list, which is a list of the items that are remaining to be done, so the contractor has something of guidance that he knows he needs to do before he's released from the project. And as the engineer in charge, you need to assure that as-builts have really been prepared, not just at the end, but all the way through the project. So in design, we have a lot of standard details and references, and again, these are often slapped on the plans along with all these standard construction notes. And often in the design, in the office when they're being designed, these things are kind of, I won't say overlooked, but a lot of attention is not paid to them. And a similar event happens in the field. A lot of times the inspectors and the contractors, they don't pay a lot of attention to that. They just look at the plans and see what it is they're trying to build. But these things almost become like a background noise, but that shouldn't be the case. These standards are usually prepared by committees, and they often originate because something undesirable happened, and it's recognized that this bad thing shouldn't be repeated. There's a wealth of information in these standards, and it's really important to become familiar with them, and that should almost be second nature to you to use that. And with that, is there time for any questions?
Very good presentation, Charlie. Thank you very much. We do have 5 minutes for questions that I believe Jennifer is going to pose. I think there's several.
Yes, Charlie, you do have a couple questions. The first question is regarding apparently some proposed legislation on concrete. The question is, any issues with eco-friendly concrete mixes, as has been suggested in recent Maryland legislative bill?
I can't say that I'm familiar with what these eco-friendly concrete mixes would be. When concrete, I mean, there's years of experience with concrete now, and as I pointed out earlier, there's a lot of admixtures that can be placed in concrete. Maybe they're not eco-friendly. You want concrete to be durable. Usually when you place it, you expect it to last for 50, 100 years or more. And I guess I would need to know more about what is actually involved in eco-friendly concrete to make a better comment on it.
Yes, okay. Another question here for you, Charlie. Is there a time frame or rainfall amount for inspection of new dams or spillways after construction and before acceptance?
Well, on a typical construction contract, usually the contractor is required to warrant their work for a year. So I don't know, again, that that's spelled out as an inspector. I know when erosion and sediment control, after every rain event, the erosion and sediment control devices are supposed to be inspected, and a log is supposed to be kept of that. And certainly a good contractor, he's going to be following the weather very closely. When I went to college, I even took a course in meteorology myself because I knew it would be useful. You have, again, especially when you're working in the run of the river, you can have a very large drainage area that's coming down your construction site, and you don't want to leave your equipment or materials sitting in a vulnerable location. So there's not a prescribed time period, but during active construction, this is part of the risk of construction. I talked about at the beginning of the presentation where things happen, and a good contractor is going to be paying very close attention to it. And if you're looking at a higher significant hazard structure, every effort is going to be made to button down the hatches, so to speak, before a rain event occurs.
Okay, there's another question that Hal answered. I'm going to let Hal answer it again verbally, but first let me ask it. Since there is a potential to create fines while compacting sand used for filter diaphragms, which compaction methods and specifications would you recommend to avoid crashing of the filter material? Hal, do you want to answer that question?
Sure, I can do that. It was a mistype at the end. It should be crushing of the filter material. Certainly, if you take sand and run over it a bunch of times with a big heavy roller, it's going to potentially break down into smaller particles, and you might actually plug the voids in the filter that you're trying to create. So NRCS has a recommended compaction method, which involves flooding the filter zones with potable water, and potable is important because you don't want to use muddy water from a local source that might fill the voids with silt. Use clean water and flood it, let the water drain out, and then briefly run over the top of the filter material with a small vibratory compactor. That minimizes the damage to the aggregate particles.
I could add to that too, that technically when you're compacting sands, it's usually referred to as consolidation, and they have other types of testing besides the Proctor test, but most people are not knowledgeable about that, and it's rarely used. Again, the amount of moisture isn't as critical as the fact that you compact it at the that you run the consolidation effort over it at the same time that you've placed the water, and not overdo it, but you're kind of jetting it or vibrating it in place.
Okay, I don't see any other questions specifically for Charlie. Ray, I don't know whether you want me to ask the question that was asked previously today. There's one more that we haven't answered.
Sure, go ahead. We got time.
Okay, it was asked, I believe, of Scott, but anybody who wants to answer. The question is, this synthetic turf, I guess it's a picture that Scott was showing, looks like plastic pollution source in our waterways. Is it approved in Maryland for this use despite this? Scott, I guess that's regarding a synthetic turf.
Sure, yeah, that's the hydroturf. I can take a stab at it. Maybe John or Hal can piggyback on it, but as far as from a safety perspective, it is approved for use because it's been shown in the laboratory tests that it can withstand, considerable overtopping flows. As far as what stakeholder, concerns would come out through the public meeting process where, these concerns could be expressed, we would, at the department, would take that into consideration, but I don't believe that it would easily fray into the waterways. At least that's not the intent whenever a dam owner would choose to put this on their embankment.
It's important to note, Scott, you're right, but it's important to note that hydroturf is actually filled with concrete, so it's not pieces of astroturf on a dam that can wash away. It's actually weighted down with the concrete that's mixed into the fibers of the turf. John, you got anything you want to add?
I do not. Thank you.
Okay, there are a couple questions that were asked yesterday that we didn't get to, and I think we have a couple more minutes, so I'll ask the first one. I think this was for John, and it had to do with, looks like issues regarding maybe climate change in our design criteria for design storms. The question is, rather than getting rid of the 5, 10, 20, and 100-year storms as design criteria, might it not be a good idea to redefine their meaning based on current up-to-date precipitation data?
Yeah, that's a great question. And actually, I don't recall who mentioned this yesterday, but we are pursuing, and I believe we actually have obtained grant funds with a multi-state kind of mid-Atlantic consortium of states to update the NOAA Atlas 14 data. So that will update both the rainfall depths and the rainfall distribution curves. And that's similar with the PMP, and not, I'm a dirt guy, not a water guy so much, but the depth of rain is certainly something that's important, but that distribution of the storm event plays a huge role into the actual inflow hydrographs into the dams and small ponds. And so we're working on that. I mean, that's something that is a big process because it's updating a national for a federal government's the Atlas 14 data. But even beyond that, I believe Howard County has a storm that they're asking people to review for stormwater management. That's, the quote Ellicott City storm, which is like, so they're looking at a 3-hour duration, high intensity storm. So all of those things are out there. I think as we get more information and data, as we get new federal government or state-sponsored precipitation updates, we'll be better informed, and that is a perfect tie-in because stay tuned because Scott's going to be talking about update to the statewide PMP right after this.
Okay, there's another question here for, I'm not sure who, anybody. Does the engineer in charge for a dam project have to be approved by MDE? In other words, how would we get started on a project to be able to submit for review with a JPA if the engineer in charge for dam design needs to be approved by MDE?
I can take a stab at that, and I'd welcome anybody else to chime in. Yeah, the engineer in charge does need to be approved by us, and to be quite honest, it's difficult for a lot of reasons, as one can imagine, for us to disallow an engineer. But it is something that needs to be approved. So what we will sometimes suggest, there's been a few cases when clearly the engineer, not to say that they aren't qualified or a good engineer, but perhaps the scope of the project extends beyond their level of expertise. So we have advised in those cases, the owner needs to bring on a second specialty, let's say, to supplement and kind of make it an engineering team as opposed to one person. A project that comes to mind, and I'm not going to name any names, the person is a perfectly experienced kind of civil designer, but they did not have geotechnical experience where that was certainly needed. So the owner, we worked with the owner, and they kind of formed an engineering team with this civil designer was still on the team, but supplemented with a geotechnical engineer to ensure that everything was up to snuff.
Okay, we are out of time for this session, so we're going to go ahead and take our 5-minute break, and we're going to reconvene at 1:10. And up next, as John mentioned, is going to be Scott Bass with an introduction to Maryland's PMP update. Scott, I can see your presentation. It looks good. You want to do an audio check, please?
Sure. How do I sound?
You sound perfect.
Okay, welcome back. Hopefully everybody can hear me. If not, maybe Ray could let me know. But assuming that everyone can hear me, welcome back to the last technical presentation of the Maryland Virtual Dam Owners Workshop. Thanks to everybody who attended and left, and a special thanks to everybody who attended and is still sticking around. We still have a great crowd here. So my final presentation is an introduction to the Maryland PMP update. And this is an introduction because the PMP update hasn't taken place yet. It's in the initial stages, as Jennifer alluded to previously on Tuesday. Before I get started, I'll reintroduce myself. I'm Scott Bass. I am a water resources engineer with Dam Safety. I've been here 4.5 years. In hydrology and hydraulics, and I just want to emphasize that I am not a meteorologist, and the PMP is the domain of a very specialty of hydrometeorology. So we use the products that the National Weather Service and some very specialized consultants put together, and then we put that to use as engineers. So I'm speaking as much as I know about it, with the caveat that I'm not a hydrometeorologist. So brief outline. First, we'll get into a definition of what the PMP is, how it's currently computed in Maryland, a few real life examples to kind of hammer home that, yes, this is a real thing, even though it's the upper boundary of what could physically be expected to ever occur. Then I'll get into kind of the new state of the art, which is state and basin specific PMP studies, which will be a lead into the PMP update in Maryland. So first, what is the PMP, this probable maximum precipitation? And a definition from the HMR 51, which was stands for Hydrometeorological Report number 51 through the National Weather Service and NOAA, defines the PMP as the theoretically greatest depth of precipitation for a given duration that is physically possible over a particular drainage area at a certain time of year. Slightly modified in HMR 55A, physically possible over a given size storm area, so not just the drainage area, but it's, you know, part of a storm. So the Hydrometeorological Division conducted these studies across the country, with the first one being in the Tennessee Valley area, the HMR 41, or I guess maybe up north in the 39. Like I said, it was completed for our region in 1978, and HMR 51, which applies to us, also applies to most of the continental U.S. east of the 105th parallel, right here, or I'm sorry, meridian, 105th meridian. And then west of that, obviously, the Rocky Mountains have some interesting dynamics as far as weather goes, and the final study was completed, HMR 59, in, I believe, the late 90s. But we still use HMR 51 today. So, okay, well, what is the PMP and what does it mean to us? If you've been to all these seminars and you're a dam engineer, a dam owner, you might know that we have 3 classifications of dams. We have low hazard, significant, and high hazard. And those are based on the impacts that would be caused by a breach of the dam downstream of the dam. For low hazard dams, we design for the 100-year storm. Significant hazard, half of the probable maximum flood. You might notice PMF is different than PMP. And high hazard dams, we design for the probable maximum flood because loss of life has been deemed to be unacceptable. And I'll just add, we designed to the PMP and PMF because overtopping is assumed to fail the dam. And if you were around for the first presentation, you might understand why. Okay, so let's break down really quickly PMP versus PMF. So as I stated previously, and I'll restate again, the PMP, the probable maximum precipitation, is the theoretically greatest depth of precipitation for a given duration that is physically possible for a given size storm area at a particular geographic location at a certain time of year. Ooh, That's a lot. And corresponding to that, in a lot of cases, is the probable maximum flood, which is the flood that may be expected from the most severe combination of critical meteorological and hydrologic conditions that are reasonably possible in the drainage basin under study. So how is this different? Well, for the most part, in our area, the PMF results from the PMP rainstorm over a saturated drainage area. But you can imagine in places with heavy snowpack, and maybe this would apply in Western Maryland, you might want to check that, let's say the 100-year snowpack with a maximum snowstorm that could fall in March wouldn't have an increased runoff as opposed to the PMP in a summer day. And this is a difficult process that requires a lot of engineering judgment. And I'll just say for the most part, modeling the PMP in Maryland results in what's considered the PMF. Okay, so hydrometeorological report number 51. How does this work? Well, it gives depths of rainfall for a given duration over a storm area, and those storm areas range from 10 square miles up to 100 or 10,000 square miles, and the durations range from 6 hours to 72 hours. For instance, this particular figure is for 72-hour 10 square mile drainage area. But for most dams and stormwater management facilities in Maryland, the 6-hour 10 square mile map is what we're looking at, which corresponds to roughly 27 to 28.5 inches of rain in 6 hours. So this is a slide that I borrowed from my first presentation just to hammer home the point. Again, this is Montgomery County, a 100-year storm, 8.2 inches in 24 hours, according to Atlas 14 data. And this is the PMP for a 6-hour storm at the same location, according to HMR 51. And over 24 hours, that would be expected to be 35.5 inches, which is an incredible amount of rain. So what's in HMR 51 and how did they compute this data? Well, I'll make note that all of the storms and data points that were used to create the HMR 51 occurred. So these are storm events that they used as, their data points. All of these occurred prior to 1971. So you might be thinking, wow, that's 50 years of data since then that we're missing out on. Not to mention all the technological advancements, which I'll get into. But they take these, the basic process is, and again, I'm just dabbling here, is that they take these storms and they have a general location in the continental United States that is subject to a storm type. It might be a tropical storm or a local storm, etc. And then what they do is they maximize the moisture content of that. Okay, maybe this was an intense rainfall, but could it have been worse? Was there more available atmospheric moisture at the time? That's called moisture maximization. Then they can transpose that storm to different similar geographic locations. And then they create these envelopments that basically, quantify, how that rainfall could apply across the United States. And as you see, this is a huge swath of the US with not many storms to make those general maps. Another issue with the stippled area, and before I get into that, just notice how generalized these contour lines of different rainfall depths are for a huge swath of the United States, which is an issue. And there's also this issue with what's called the stippled area, which is this kind of gray area here. And what the HMR 51 says about that is, well, first you might note that this corresponds to the Appalachian Mountains. So let's see, what does this say about this? So they have a disclaimer that says this stippling outlines areas within which the generalized PMP estimates might be deficient because detailed terrain effects have not been evaluated. And basically what that means, and again, this is my basic understanding, is to get intense rainfall, you need uplift. You need a gradient from the upper atmosphere to the Earth's surface as far as temperature goes, and you'll get, if you imagine an anvil cloud, that's kind of indicative of that upward motion of air, which leads to condensation and then rainfall. So what can exacerbate that process are big mountains or anything that can, you have a fast moving front, it crashes into the mountains and exacerbates that updraft. So within that area, you're supposed to do like a basin specific model. But the problem is that's a large portion of Maryland, which encompasses our 3 western counties, which we have our largest dam in the state of Maryland, and some other really significant dams. So this creates a problem for the state. In the late 1980s, U.S. Army Corps of Engineers created a program called HMR 52 that allowed us to model the data that was in HMR 51. For small dams in the state, we typically use the 6-hour depth from those graphs and then use a particular rainfall distribution to model of runoff through the dam. For large dams, though, greater than 10 square miles, it's necessary to use this HMR 52 program so you don't overestimate the flow from a probable maximum storm. And so this is the third PM acronym, PMS. This is probable maximum storm, which basically maximizes the worst case for your drainage area, and I'll get into that. And in June 2019, HEC-MET view came out from the Hydrologic Engineering Center out in Davis, California, which modernized this process. But so this is what I'm talking about with the probable maximum storm. These are all different areas, like the innermost is a 10 square mile area, and that goes out to your different storm sizes. And the probable maximum storm centers those worst rainfall amounts on top of each other. And then what this program allows you to do is orient that probable storm over your drainage area such that the worst possible rainfall is delivered to the drainage area. And that's how we model the probable maximum flood. And this is what HEC-MET view allows us to do. It just brought it into the 21st century and allows GIS to compute this for us. So HMR 52, it's an old DOS program. You enter XY data for the drainage area outline, and you can kind of see this inner isohyoidal. This is the 10 square mile drainage area centered over that oblong watershed. It then creates a runoff amount that you put into your HEC1 or HEC HMS program and route it through your dam. So this kind of shows that it's a simplified version of this northwestern oriented drainage area, and it does a decent job of modeling it in a DOS program. It also allows you to center a storm over a particular watershed. That would be the green one, which goes to the dam. The brown ones are downstream drainage areas, and you can extend those isohyoidals to those downstream drainage areas too, and model rainfall that way. Again, HEC-MET view made this a lot more convenient, although some engineers have told me it's a difficult process. You just put this into GIS rather than an XY points into a text file, and it'll take care of that for you. Let's say you're in the stippled area, you might have to create a basin-specific probable maximum flood study or PMP study. This is difficult. You need to hire a meteorologist or have an experienced engineer who's done these studies before. This is one that was done for the Susquehanna River and support of the Conowingo Dam. So that's my spiel on the HMRs, because we're still using those, and I want to Before I highlight the age, I wanted to just thank the hydrometeorological center for these studies. I think as I was preparing this presentation, I was thinking, the data that or being able to model and quantify the PMP has probably saved countless lives in the United States just because of the dams that were constructed since then in areas that have received intense rainfalls, probably can withstand a big enough storm, whereas before that data came out, we might have kind of been in the wilderness. So thank you, NOAA. And again, so just a fun timeline. HMR was completed, 51 for our area was completed in 1978. We are still using data from that. And as I mentioned, in 1971, that was the last storm that was analyzed. A couple things that have happened since 1971. In 1974, President Nixon resigned. 1975, Microsoft was founded. 1978, they finally finished the HMR 51 study. In 1979, NEXRAD Radar Joint Systems Program Office was put into place to set up NEXRAD radar system. In 1983, Hal Van Aller joins Maryland Dam Safety. 1989, Scott Bass is born. In 1992, the first NEXRAD radar was installed. 2007, the iPhone was released. In 2021, as I mentioned, Microsoft was founded around the time HMR was started. In 2021, we are having a virtual dam safety conference using Microsoft Teams that you may be watching from your couch. And in 2021, we are still using HMR 51 in the state of Maryland to model the probable maximum precipitation. So I thought that was fun. You may disagree. So let's have some real world examples of probable maximum storms and precipitations. So you may remember Hurricane Harvey in 2017 delivered 60+ inches of rainfall in the matter of days to the Houston area. This set record. This is by far the worst tropical storm that the United States has ever seen, and is on par with any other storm that the world has seen. Again, pretty incredible amounts of rainfall. Like I showed you, those 10 square mile drainage areas with intense rainfall. This was intense rainfall over tens of thousands of square miles. So the state of Maryland probably fits in that blue area where 25 inches of rain was delivered. You may say, okay, well, that's the Gulf of Mexico. That's warm waters. We don't experience that here. But if you remember Hurricane Florence in 2018, this delivered upwards of 30 inches of rain in the matter of, a day and a half, 2 days. And if you recall, this at one point was threatening Maryland so much that the governor declared a preemptive emergency. All the dam safety staff was at the annual conference in Seattle, and we were flown home early in the event that it would have hit Maryland, and luckily it didn't. This just shows a wide swath of the state of North Carolina that experienced greater than 1,000-year return interval rainfall depths over the matter of a few days. Okay, so those are some real world examples to bring home that these are real threats. And let's move into the future a bit and talk about state-specific PMP studies and tools. So adjacent to Maryland, in 2015, the state of Virginia completed a state-specific study. And as part of that, they have a summary report which outlines the methods. Since then, they've pre-run the PMP for all of their significant high hazard dams, which is incredible. And they have a GIS tool that allows you to extract that information for use in an engineering study. In 2019, the state of Pennsylvania completed the same, and they have similar tools available to them. So taking a look at the state of Virginia study, here's a map of their new PMP. You can see it isn't a generalized map like the HMR studies, but you can actually kind of see the topography reflected in this. And while I'll caution from from drawing conclusions from this study for the state of Maryland. I will just say for Virginia, the results showed a decrease from the HMR studies in the western portions of the state, with some interesting things happening at the crest of the Appalachian Mountains here, and an increase from the HMR studies to the eastern portions of the state due to intensifying tropical storms and better understanding of those storms. You'll notice a little bit of overlap to Maryland, but I'll note that this stops at the crest of the Appalachian Mountains in Maryland here. There's Backbone Mountain, Meadow Mountain, and to the west of this, you could have some interesting dynamics with that uplift that I talked about earlier. So I hesitate to draw conclusions about our state till we have a study of our own. Additionally, the Pennsylvania study was completed in March 2019. So a quick comparison that they have in this report, and I pulled this directly from it. The benefits of this now is a far more robust storm analysis system with higher temporal and spatial resolution, basically computing power. Like I said, Microsoft was founded basically at the time HMR started. Look at the computer that's in your pocket everywhere you go today. That is a mobile smartphone. We can leverage this in these studies, and they have. Improved understanding of climatology's moisture, content in the air, all these processes that drive extreme precipitation, and a greatly expanded storm record. Like I said, all the storms in the HMR prior to 1971. An additional benefit of these state-specific studies is it takes care of that stippled region. So they are able to actually consider the topographical effects. And let me read the exact thing. The geographic transposition factor, the GTF, provides explicit evaluations of the effect of terrain on rainfall and corrected for the lack of analysis in the stippled region of HMR 51. So this, if we would have one of these for the state of Maryland, it would benefit, definitely dam designers and definitely dam owners, and also the citizens of the state if they're living below a dam that, might be underestimated for the PMP, or it might benefit dam owners if the PMP is overestimated by the HMR 51. It's kind of a mixed bag. So just an example of the storms that were taken into account in the Pennsylvania study. This is a map in their report. They break down different storm types. Red is local storms, which I'll define in a little bit. Green, general storms. Yellow, tropical storms. These are extreme rainfall events. So local storms in the PA-PMP analysis, just to show you how updated the information is, here's Ellicott City flood of 2016 that they considered in their study. I imagine our study might be able to consider the more extreme 2018 study. And I'll highlight this Smethport study here, which some of you may recognize the name of Smethport. But local storm is defined by a storm event that occurs over a small area in a short period of time. Precipitation rarely exceeds 6 hours and covers less than 500 square miles. Frequently, they'll only last 1 to 2 hours, and precipitation will occur over areas of up to 200 square miles. So these are very isolated, thunderstorm events. General storms. I don't recognize any of these off the top of my head. Some of you might, though. A storm event that produces precipitation over areas in excess of 500 square miles and is associated with major synoptic weather features, big gradients and pressure in the jet stream and whatnot. So they have a great database of these types of storm events. And finally, tropical storm events. As I talked about, Florence in 2018, they considered that for the PMP study and actually drove the PMP in the eastern portion of the state, if I'm not incorrect. Okay, there's also, in preparation for this presentation, I looked into that Smethport storm, and if there's any water resources engineers here who went to the University of Maryland, you've probably seen this in Dr. McEwen's class, because he's been teaching at the University of Maryland since probably around when the HMR was completed in the late 1970s. And Smethport set the world record for rainfall in the 3 to 4 hour range, and it was about 35 inches of rain. It's right here. This is the world record curve for durations. And I'll note Harvey falls on this world record curve too. This is just a 1992 figure. So what they did as part of this study is they updated this Smethport storm using current methods and current tools for hydrology and meteorology. They used the HEC HMS model, etc. So the problem with this storm is that it drives the PMP across basically all of the East Coast and especially in the Appalachians because it's so severe. The question is, how good was the unofficial records that were recorded back then? A lot of the observable data consisted of, basically a farmer or, a man in town who had a bucket outside of his porch or outside on their lawn, a bathtub maybe. They went out after the storm was done and the bathtub or the bucket was full or overflowing, which they could measure the height of the bucket, etc. But there was a lot of these unofficial buckets that kind of verified. It wasn't just one guy who reported 30 inches. It was hundreds of people with bucket studies showing a considerable amount of rain. And so what they did is they took all these studies, they plotted them out, and they tried to get a modern understanding of the storm using maps, GIS, etc. And so to show you what HMR 51 did with this storm, as I said, they can transpose the storm over different areas of similar geography. And this is the generalized area they did it in the HMR 51. But the new study said, okay, well, really only this area is similar to the Smethport area. As you see, it overlaps into the western corner of Garrett County. So Virginia study ended to the east of the Appalachian Ridge that drains the Potomac. What this study is saying is that the western portion of Garrett County could be susceptible to the same conditions that led to Smethport. So looking at their map for 10 square mile precipitation maximum, in general, the PMP goes down from HMR 51. But another benefit of these state-specific studies is that we have an improved resolution of these things, and we can actually go to 1 square mile. So if we move to the 1 square mile map, we can see the impact of Smethport, since it was a very isolated local storm. And so until we have a state study that can resolve what's going to happen here, it could be that the eastern portions of Garrett County could see an increase, the western portions could, or I'm sorry, eastern portions could see a decrease in PMP, western portions could see an increase. And that's all I'll say about that, because a Maryland study might show that, oh, this is actually the Appalachian Plateau. It's, but I'm not a meteorologist, so I'll caution any more conclusions for the state of Maryland based on the Pennsylvania study. You can do what you wish. And so since the Pennsylvania study was, updated with Hurricane Florence with an upgrade to the understanding of the Smethport storm, there is some variance in areas of where they overlap. And the Pennsylvania study talks about this. Some areas it increased, some areas it decreased with the new information. As you can see, those overlaps are right over the state of Maryland. So I encourage you, if you're interested, to look at that for yourself and draw your own conclusions. But I will not make any promises for what a state-specific Maryland study will do as we calibrate these studies and transpositions specifically to our state. So I think this is my final slide. The good news is that Maryland has been awarded a grant to move forward with a probable maximum precipitation study for the state. The first third of this has been funded. We're working towards the second portions, but it might just take a while. And that's exciting news to me. I hope it's exciting news to you. I think many dam owners will benefit from more realistic estimates of PMP. And if in some cases the PMP goes up, I think the residents of the state of Maryland will benefit from better designed dams. One other thing I'll say is there might be some temporal distribution effects that counteract the increase in rainfall depth. So how the HMR 51 put the rainfall together is very conservative, and it basically lines up all the intensities right on top of each other. The state-specific studies might show that those were overly conservative, but again, we'll have to wait and see till the meteorologists weigh in. And with that, are there any questions? But I think Ray might roll right into the questions and wrap-up segment, and we'll go from there. I encourage you to stick around for just a little while longer if you're still hanging on. And Ray, if you're on, I believe you're muted.
Okay, can you hear me?
I can hear you now. Yep.
Very good. Thank you very much.
Hey,
Yeah.
Ray, there's an echo again. Not sure why.
Testing 1 2 3. Testing 1 2 3.
Okay, that's better. Thanks.
Very good. Okay, let's keep rolling. The session goes until 2 p.m. Good afternoon. My name is Ray Barr, Deputy Program Manager of the Sediment, Stormwater, and Dam Safety Program. We would be remiss not to acknowledge today a giant in Maryland's Dam Safety Program, Harold Van Aller. Whereas Hal has been with Maryland's Dam Safety Program since the 1980s, when the specialty has come into its modern discipline. Whereas Hal has a passion for dam safety, and his expertise spans from technical to practical, always ready to lend a hand and get the work done. Whereas Hal has helped to establish the geotechnical and structural engineering backbone of the program. Whereas Hal has set up the electronic databases and the SOPs that are the beating heart of day-to-day operations. Whereas Hal is well versed with the operations of dam safety programs from across the country, bringing that knowledge back home to use in Maryland. Whereas Hal has been involved with ASDO since its inception and is currently on the board of directors as the past president. Therefore, Maryland's Dam Safety Program is well positioned to continue in Hal's absence due to the pioneering efforts of his career. And while his in-depth understanding of how things came to be will not be replaced, the platforms that he has established will serve Maryland dam safety for years to come. So Hal, we have invited some of your close friends and the secretary of the department and the governor to send you off with this following proclamation. The citizens of the great state of Maryland and the governor would like to thank Hal Van Aller for 38 years of wonderful service in Maryland's Dam Safety Program. Mr. Van Aller worked initially as a soil conservation service intern, and then for over 30 years as a dam safety inspector, and finally as the division chief of Maryland's Dam Safety Program. Hal has been recognized locally and nationally for his expertise in dam safety engineering, but just as importantly, for his kindness and humble leadership. While Mr. Van Aller's public service to the state will be missed greatly, he should rest assured because of the institutional legacy that he has helped to establish and the invaluable training that Maryland's dam safety community has gained from working by his side. How? Maryland's dam safety program couldn't be better. So I'd also like to share with you some remarks from some of Hal's colleagues over the years that you can read on this slide. And I also believe that Charlie has a short story that he would like to offer at this time.
Okay, I'll try to keep this brief. I've been working with Hal for 15 years now, and a number of those years we were pretty short staffed in Baltimore, down to about 3 people. And so you get to know a guy after a while. And Hal's a farm boy. He's always tinkering with things. If he goes out to a dam and it's a corrugated metal pipe and it looks a little wobbly to him, he'll shake it to see if it stands up. If there's a valve that hasn't been operated, he'll go and he'll try it to see if it'll open. Sometimes it opens and you can't close it. There's a lot of things like that. He's very investigative. And it also comes down to electronics and those types of things. I remember a number of years ago when we were all getting cell phones, and then the cell phones were following these voice commands. You could say, call such and such. So we could be driving down the road and he could give a voice command and do that while still driving. A lot of times we had limited number of vehicles, and Hal would have the state vehicle, and he would pick me up. And then we would go do some inspections. And for whatever reason, though, with his voice commands, he could never reach my state cell phone. When he'd say call Charlie, it would always call my house phone. And inevitably, my wife would always have to pick up and answer it and say, you got the wrong number, Hal. He didn't get his state cell phone. Well, this went on for a couple months, off and on. And then one time, my wife kind of got the best of him. He had called, and it inadvertently again went to my house phone. And she says to him, Hal, if you keep doing this, I'm going to have to tell Charlie. So about 5 minutes later, he walks into the office, and I was in the office, and we looked at each other, and the poor man just hasn't been the same since, because he knew that Vicky had called me. So Hal's a great guy. He has a good sense of humor, and he's very dedicated, but his tinkering sometimes gets him into a little bit of hot water.
Great, thanks, Charlie. Does anybody else want to say anything at this time before we move on to Q&A?
I just want to say thanks, Hal, for being a great mentor in the field of dam safety and a great example for what, Maryland, I think, is widely recognized as one of the best state dam safety programs out there in the country, at least within the industry. And we owe a lot of that to you. So we've got big footsteps to follow, but I think you've set us up in a great position for that.
Okay, I know this is somewhat anticlimactic, but Hal wanted to make sure that we got through all of your questions today before he left. So we're going to continue by answering as many questions as possible so that we can record them for future use. That is, as long as Microsoft Teams allows this session to continue. So I'm going to start off with the first question. In light of Hal's departure, how timely, are you planning organizational changes? And will the dams assigned to Hal be reassigned? And how will this affect the EAP updates due on May 1st? So I'm going to assign this question to Ray. Go ahead, Ray. So the answer to that, Gene, is no. We reorganized for the future last year when we divided Maryland's dam safety program into 2 divisions, the permits division and the inspection and enforcement division. And this was to improve program efficiencies, and it's worked out really well. Hal is currently the division chief of the inspection and enforcement division, and the department will fill this position once Hal retires. His dams will also, I believe they've already been reassigned to existing staff, and if they haven't contacted you yet, they will very soon, and definitely before the EAPs are due on May 1st, so that you can update your contacts. Next question. I think I'm going to get some help from Jennifer on this one.
Okay, this is a question that anybody could answer, I think. Are yearly dam inspections by MDE done by lottery each year? I've run across numerous farm dams that have trees well over 20 years of growth, which obviously shows inspection has not been done for years. Anybody want to take that one?
Anybody in the inspections division want to take it?
Well, this is Hal. I guess I can take that one. Now that I've got my composure back, I'm humbled by all the comments that I got. Anyway, thank you. So farm ponds are not normally on our radar for inspections. A lot of farm ponds are approved by the soil conservation districts, and we don't even know about them, so we don't inspect them. The landowner, as John has pointed out, and other people have pointed out, the owner of a dam is responsible for it. And all the small pond approvals that the districts issue include an operation and maintenance plan that the farmer or the owner is supposed to follow as far as maintaining vegetation, not allowing trees to grow within 15 or 25 feet of the dam structure. And once in a while, we'll get a call to inspect such a structure. Usually it's coming as the site is being developed for subdivision, and the dam or pond is going to be turned over to an HOA. And this is where Jennifer said that the developer has a responsibility to fix up that dam before it's turned over to community property, because HOAs typically have very limited resources and can't take on upgrades or repairs to dams.
Okay, next question. I'm gonna shoot this one to John. Excuse me. John, this one is for you, but you're allowed one pass, but you have to name who should be answering it. Here it goes. If a dam owner fails to respond to an NOV or other written direction from MDE Dam Safety, does MDE Dam Safety have the authority to contract the work to be performed and then invoice the dam owner for the work? If Dam Safety has the authority, have they ever executed it?
Yes, I'll happily answer this one with a quote from a famous dam safety engineer from Virginia by the name of Mr. Charles Karpowitz. You must maintain or we will drain the pond. If you know Charles, you've heard the quote before. But yes, the department has the authority under Environment Article 5-509 to assume control of a dam or reservoir and render it safe if the owner does not act in a prompt manner. We have the authority to contract with whatever firms are needed under emergency procurement laws to have the work completed. And once the work is completed, we will file a request for payment from the owner. And if they do not make that repayment, we can put a lien on their property to force repayment. That being said, we have, well, I would say I think once or twice in the 80s and 90s, we did this. But we haven't gone to the extreme of doing it recently. That being said, we have gotten right up to the line. And, you know, fortunately, things prevailed and we didn't have to exercise the authority. But if we have to, particularly if it's an extreme case of public safety, it's an option on the plate.
Okay, I'll ask the next question. What outreach or training is available for Maryland utility companies to improve safeguards around utility work and dams? What are their existing legal obligations? Does anybody want to take this one? Charlie, maybe?
Well, It's one of those things you try to make contacts with people. I mean, we're putting on these workshops like we're doing today. It's all a struggle, but yeah, I mean, we are trying to outreach to everybody, and certainly the utility companies are up there with that. And that's one of those things that we got an area for improvement.
I can provide an example on a project that's about to be permitted, but not yet, where it is a roadway embankment with multiple utilities in it, including a very large WSSE transmission main. We worked with the owner, and they're actually going to place signs on the dam embankment, like you would see for a petroleum or natural gas distribution pipeline. You know, it's our fiber optics. That indicates that this is a dam embankment. Don't dig. First call this phone number, which would be our dam safety phone number. So that is something that it's not regulation or law. It's pretty good practice, I think. So we would encourage dam owners to develop signage of that same nature, because ultimately the owner of the dam, you know, needs to control that work that happens on it, whether that be a state or county or local roadway. So if they have somebody else digging into the dam embankment that they own, that causes a problem, you know, there's multiple levels of liability and who can be sued, and sure, everybody will be sued if there's a problem, but cheap way to avoid it is work with your sign shop and develop some signage to alert people that this is a dam embankment.
Okay, the next question is going to be for Hal, because I've heard him answer this one numerous times throughout the years. Hal, do you have a list of recommended engineers within Maryland?
We do not have such a list. We are not able to recommend any particular engineers. If you have an engineer in mind or several engineers and you want to call staff at the Dam Safety Division and discuss them, we can certainly provide some personal experiences, but we can't endorse or any particular engineer. We can't show any favoritism. I know that Montgomery County has a list of engineers that are involved in pond maintenance, and that would be a starting point to look at the engineers on that list. But we don't have any such list. And I can tell you that some states that do have lists of engineers, the states do not provide any guidance whatsoever. It's a self-registered, self-certified list. So anybody that can call into their state's website and put their name on the list, they just check a box that says, yes, I'm qualified in dam design and construction. And it ends up being just a list of all the civil and environmental and geotechnical engineers in the state. So it's really not been much help. But if you have any questions, be sure to give us a call and we can certainly point you in the right direction, hopefully. Okay.
Okay, I have a question for Charlie, I think. Is there a way to use sequence of construction in urban settings on weirs or large structure construction on a significant hazard dam to reduce expensive impacts without creating a detriment to dam stability?
Well, I mean, sequence is certainly important. Again, you don't want to have two operations occurring simultaneously. That's a very broad question without having more specifics. One of the interesting things is there's a number of high hazard structures in the largest city in Maryland that are they have active construction going on around them right now, and we've had to activate EAP level 2 for these just as a precaution, not that anything went wrong, and everything's been going very smoothly, I may add. But it's amazing how the left hand doesn't talk to the right, and you need to have the emergency managers understand that there is activity going on at a dam, be it high, significant, or whatever, and so that they're aware of what you're doing so that they can be prepared if they have to take action. But yeah, the sequence is very important, but you also got to have some flexibility in it because you can still encounter things that you didn't anticipate.
Okay, this next one's going to be for John. First off, somebody asked, are the draft small pond approval changes available to the public? Yes, they are. We'll go ahead and put that up in the link for the cold water, the regulations that are changing the cold water approval. So here's the question. I have heard that our local SCD will no longer be approving small ponds starting in 2022. Can you please clarify?
Yeah, that's a, I don't want to necessarily say it's a rumor, but it's been floating around quite a bit. Let me give some context for people who have heard this and what it may or may not mean. So at the January, I think, of this year, the NRCS office, the state conservationists, put out a memorandum to all the districts that indicated that they will not, as of next year, January 1, 2022, they do not or will not accept basically a full technical review of small ponds. So there's some counties in the state or some districts where they may not have the technical expertise to do the review, or there are other certain NRCS requirements that prohibited them from doing the review. So they would ship it to one of the larger NRCS offices in the state, and basically those engineers would do the whole review and ship it back to the SCD and said, go ahead and approve it. But due to staffing and just resource limitations, the state NRCS office basically said, we're not going to do that anymore. We can help you out if you have technical questions, but we can't do the whole job for you. So what does that mean? Well, it means a few things. It means there's a void, there's a vacuum to be filled, and we're committed to stepping in, you know, with all the resources that we have available, sometimes limited, to help fill that void and provide technical assistance to SCDs. You know, I don't think we're positioned to have an SCD send us an entire application package and say, please tell us if we can improve it. We would probably say, well, we're just going to issue the permit ourselves then. But, you know, if you have technical questions or issues, we can be a resource to that SCD. So that's how we're trying to fill that void. We're also kind of concurrently working on some memorandum of understandings or agreements between the NRCS and the districts to kind of formalize a little bit more policies and procedures and perhaps oversight over the districts, because the delegation of small pond approval authority to the districts has been kind of a de facto part of law. It's not explicitly written into there, but certainly Maryland Department of the Environment retains the regulatory and legal oversight requirements of that. So we're trying to improve the process, I think, and ensure there's good collaboration. But anyways, on January 1, 2022, if the districts don't feel that they're technically capable or they have the right staffing to do small pond reviews, I suppose they could simply say we're not doing them anymore. I haven't heard that explicitly from any single district. I think, you know, many of them will try to gear up and find ways to make it work, but it's still a process that's in motion. Many people, including us, just found out about this in January of this year, this change in policy from NRCS. So we're working to adapt, and stay tuned. If we find out more information or have progress, we will let you know, and we'll go from there.
Okay, Charlie, I have a clarification on the question I asked you before. It was not sequence of construction, it was support of construction. So is there a way to use support of construction in urban settings on weirs or large structure construction on a significant hazard dam to reduce expensive impacts without creating a detriment to dam stability?
That was a long question, and I'm trying to picture it in my mind. I mean, supportive. You could read it one more time for me, please.
Yes, sir. Is there a way to use support of construction in urban settings on weirs or large structure construction on a significant hazard dam to reduce expensive impacts without creating a detriment to dam stability?
Oh yeah, I mean, the one illustration I had, it's Lake Ashburton, and they're putting in these large water storage tanks, and supportive excavation was everything. Originally, they were trying to site that in different locations, and one of the sites considered was at the toe of the dam, and that was probably the worst place to do any type of activity, even with supportive construction. But we found a place off to the side there where they're doing it, but they encountered a lot of rock. So even though it's expensive to put that in, it's allowing the work. Once the secant walls are placed, the work is progressing very rapidly. So if you're using sheet piles where it's a less precarious situation, they go in quickly, they can come out quickly, and they can allow you to get the work pretty rapidly.
Okay, thanks everybody. That's it for today. Please go out and inspect your dam, update your EAP by May 1st, and spread the word about dam safety. Good afternoon and good luck.